What if the Big Bang wasn't the beginning of the universe, but rather the first of many explosions that will happen in the future? Astronomers are now looking into crazy ideas about how the universe could break, tear, or even quantum flip into a whole new reality in the far future, starting a second Big Bang. We might already be able to see proof of this, from the way space-time waves to the way the cosmic microwave background hides the marks of past cycles. And if these ideas are true, the next big cosmic event might not be the end, but the start of a whole new world. What do we mean by a second Big Bang? The Big Bang is what most people think of when they hear the phrase. They think of the single event that created space, time, matter, and energy 13.8 billion years ago. In current physics, however, the term second Big Bang doesn't always mean a new beginning from nothing. Instead, it refers to the chance of another universe-scale spark, which could be a restart, a return, or a change so extreme that it matches the conditions of our own birth in the universe. The original Big Bang wasn't an explosion in space. It was an expansion of space. Every point in the universe was once compressed into a hot, dense, nearly uniform state. In a fraction of a second, space itself began stretching faster than the speed of light, dragging matter and energy with it. The temperatures were so intense, trillions of degrees, that atoms couldn't exist. Instead, the universe was a quark-gluon plasma, a seething mix of fundamental particles colliding and combining in ways that would later give rise to stars, planets, and life. A second Big Bang would recreate that kind of physics: unfathomable density, extreme temperatures, and a rapid inflationary expansion. The key difference is that it wouldn't be the first time it happened. We'd be talking about a new cosmic epoch, one that could follow the collapse of our current universe, a radical phase transition in the vacuum of space, or some higher dimensional interaction that injects colossal amounts of energy into our cosmos all at once. You can think of it this way: the universe is like a live thing. It was born with the first Big Bang. If there is a second, it is not a repeat of the first life. It is the start of a new one that may have faint memories of the first one. Physicists call these situations cyclic or bouncing universes. Theoretical research is becoming more interesting because they offer ways to get around the singularity, which is one of the biggest problems in astronomy. In the standard Big Bang model, if you roll the clock backward, density and temperature climb toward infinity, a point where the known laws of physics break down. It's a mathematical dead end. But if the universe instead bounced from a previous phase of contraction, that infinite singularity disappears. Instead, quantum gravitational effects, exotic matter fields, or higher dimensional geometry step in, capping the maximum density and letting the cosmos rebound. That rebound is, in effect, a second Big Bang. And unlike the original event, a second one wouldn't be the ultimate start of time. It could be a continuation of an infinite sequence of expansions and contractions, each one separated by trillions or quadrillions of years. From our perspective inside one cycle, we'd experience it as the total destruction of our current universe. Galaxies drawn together, space collapsing, energy densities soaring, followed by a sudden reinflation and the creation of a brand new cosmic landscape. There are different ways to get to a second Big Bang besides collapsing. One is called fake vacuum collapse. The state of our world might be metastable, like a ball sitting in a shallow dip that isn't really the bottom. A change in the quantum world could push it over the edge and into a deeper, more stable vacuum. The energy released during that change could create a whole new area of space that grows and looks exactly like the Big Bang to anyone inside it. What's the catch? Everything in our world would be erased right away, with no notice. String theory gives us the idea of brane physics, which leads to another road. Our world is thought to be on a three-dimensional brane that floats in space with higher dimensions. A clash between branes could release a huge amount of energy, which would cause our brain to grow in a way similar to the Big Bang. Based on these models, these kinds of crashes could happen all the time. creating many cosmic cycles that last for unimaginable amounts of time. However it happens, a second Big Bang wouldn't simply replay the same script. Conditions could differ in subtle or dramatic ways. The density fluctuations seeded in the earliest fractions of a second might be larger or smaller, leading to universes with more massive galaxies or sparser cosmic structures. The values of fundamental constants, like the strength of gravity, the speed of light, or the ratio of electron to proton mass, might be slightly altered, shaping a very different physics and chemistry. Even the arrow of time could be reset. In our current cycle, entropy, the measure of disorder, is always increasing. If a second Big Bang manages to reset entropy to a low value, it would begin a new era of time's arrow, starting fresh. If it doesn't, each cycle could inherit some of the disorder from the previous one, leading to universes that look more chaotic over each iteration. Cosmologists don't care about poems when they try to describe a second Big Bang. Finding the exact conditions, density limits, temperature ranges, and quantum field behaviors that would lead to an expansion that is identical to the one that created our universe is what this project is all about. That means measuring the structure of space on a big scale, looking for tiny traces of possible earlier cycles in the cosmic microwave background, and finding out how space-time behaves when extreme energies are present. The long-term outcome of our world is also something to think about. Space will keep growing forever if dark energy stays the same. Galaxies will keep moving past each other's edges until the universe gets cold and empty, a heat death without a second Big Bang. The cyclic universe model. Think of the universe not as a single fireworks show, but as a heartbeat, a steady beat of birth, growth, collapse, and return that goes on for unimaginably long periods of time. The cycle universe model is based on the idea that our universe is just one in a long line of universes, each one born after the death of the last. The Big Bang was thought to be the beginning of everything. Since then, space has been growing, with galaxies moving farther apart, and the temperature of space falling over billions of years. But the cycle model changes that script. From this point of view, the Big Bang wasn't the very first event. In a much longer period of the universe, it was just the most recent change, the beginning of the current growth phase. The basic rules are surprisingly easy to understand. Expansion leads to contraction, contraction to a very thick bounce, and the bounce starts a new expansion. It's a loop that doesn't really begin. But underneath that simple loop is a web of difficult physics, from how gravity behaves at very high densities to how dark energy shapes each cycle in a way that no one knows. In one form of the cycle model, gravity is the main force at the beginning. Dark energy, the unknown force that speeds up the expansion of the universe, controls the big movements in our universe right now. The speeding up could slow down, stop, and go backwards if the strength of dark energy changes over time. Galaxies that are moving apart right now would start to come back together. There would be less space between groups, and the universe would go through a time of contraction. During contraction, the cosmos wouldn't simply run the expansion in reverse. Matter would clump together, radiation would grow hotter, and large-scale structures would dissolve into a smooth, high-density state. As the collapse continued, temperatures and densities would soar to the kind of conditions last seen in the earliest fractions of a second after the Big Bang. At this point, conventional physics would predict a singularity, a point of infinite density where the known laws of nature fail. But in cyclic models, that singularity is replaced by a bounce. In loop quantum cosmology, for example, the geometry of spacetime is quantized, built from discrete chunks at the smallest scales. As the universe contracts to Planck densities, these quantum geometric effects generate a repulsive force that counteracts gravity. Instead of crushing everything into an infinitely small point, the collapse halts and reverses. Space begins to expand again, carrying with it the energy and matter of a new universe. Other cyclic scenarios borrow from string theory's extra dimensions. In brain cosmology, our universe is like a three-dimensional membrane floating in a higher dimensional space, Another brane could be moving parallel to ours. Every so often, perhaps once every trillion years, the branes collide. The collision releases an immense burst of energy, heating the branes and triggering conditions identical to a Big Bang. From inside our brain, it would look exactly like the start of a new universe. One beautiful thing about circular models is that they can solve the problem of entropy. Entropy, which is a measure of disorder, always goes up in a one-time world. This causes a heat death where no useful energy is left. In an endless series of cycles, entropy could be weakened with each growth or pushed into other dimensions with each bounce, which would restart the clock for the next cycle. Cyclic models can also help us understand some of the mysteries of the cosmic microwave background, CMB. This weak afterglow from the beginning of the universe is amazingly constant, but it also has tiny changes that helped galaxies and clusters form. Some cycling theories say that the patterns we see in the CMB might come from changes in density in a previous cycle, which were left behind on the bounce. That is, it's possible that we are hearing sounds from before the Big Bang. It makes sense that not every turn would look the same. The conditions at the start of each growth might be different based on how the crash went. A bounce could make a universe with different values for basic constants, slightly different amounts of dark matter, or a space curve that isn't the same as it is now. This way, each cycle could be a different version of the universe, shaped by the leftovers and changes from the last one. Testing the cyclic model is no easy task. We can't simply watch a universe collapse and rebound. The timescales are far too long. Instead, cosmologists search for subtle signals imprinted in today's universe that could betray a previous cycle. These include certain patterns in the CMB, the spectrum of primordial gravitational waves, or hints of anomalies in large-scale structure surveys. Those gravity waves are used in one of the most interesting tests. If there was a previous cycle, the last few seconds of its fall and bounce could have created gravity waves that are still moving through space today. Finding this kind of signal would be revolutionary. It would show not only that the universe is cyclical, but also that our Big Bang was not the only one. The Big Bounce hypothesis. A crushing fall of the world would be the final curtain for most people. It would mean the end of space, time, and everything in between. That finish is wrong according to the Big Bounce hypothesis. A collapse could be the start of a great rebirth instead of the end of the universe. It could turn a dying universe into the seed of a new one. The main idea is easy to say, but hard to understand. The world may go through cycles of expanding, contracting, and expanding again. One day, the growth that is happening now could stop, turn around, and squeeze the universe into a very tight state. Something in the rules of nature pulls back though, so it doesn't shrink to a singularity, which is a point where space and time stop being real. The fall turns into a bounce because of that push, which starts a new phase of growth that looks like a new Big Bang from the inside. To understand why this is such a radical proposal, it's worth revisiting the problem with singularities. In the traditional Big Bang model, if you rewind the clock far enough, the density and temperature of the universe approach infinity. It's a mathematical signal that our equations are missing something fundamental. Likewise, if you run the cosmic movie forward into a hypothetical collapse, a big crunch, the same infinity problem appears. The Big Bounce hypothesis is built on finding a physical mechanism to avoid those infinities entirely. The idea of loop quantum cosmology is one of the most popular ones. Space-time is not seen as a smooth cloth in this area of theoretical physics. Instead, it is seen as a network of very small, discrete loops at the Planck scale, which is the smallest size the universe can have. Quantum geometry effects create an opposing force as the universe gets smaller and closer to Planck densities. In normal situations, this force isn't very strong, but near the point of greatest compression, it becomes overwhelming, fighting gravity and stopping the fall. As a result, a bounce, where space once again spreads out in all directions. String theory is where Ekpyrotic cosmology which is a different take on the bounce idea, got its start. This theory says that our world is on a three-dimensional brane that floats in a place with more dimensions. When one of our brane hits another, it causes a bounce. A huge amount of moving energy is turned into heat and matter in the impact, which sets the stage for the Big Bang without ever going through a singularity. From inside the brain, like us, it looks like the universe just burst into being again. The Big Bounce hypothesis also offers potential answers to some of cosmology's biggest puzzles. Take the flatness problem. Why is the universe's geometry so close to perfectly flat rather than curved? In a bouncing universe, flatness can be preserved or restored during the contraction phase, making the observed flatness today a natural outcome rather than an improbable coincidence. It also affects the horizon problem, which is the question of how different parts of the universe, which are now very far apart, have temperatures that are almost the same even though they have never met. In a circular or bouncy model, those areas might have touched during the contraction phase before the bounce. This would have let them balance out before expansion pushed them apart again. It's hard to test the Big Bounce, but it's not impossible. The cosmic microwave background, CMB, which is radiation from the early universe, might show signs of a bounce. Some changes in temperature trends, especially at very large angles, might be signs of pre-bounce physics. The range of initial gravitational waves is another possible clue. If a past contraction caused gravity waves, they might have been able to survive the bounce and are still moving through space right now. In the future, telescopes like the Square Kilometre Array, SKA, or the Laser Interferometer Space Antenna, LISA, might be able to pick up these kinds of messages. That being said, the Big Bounce hypothesis does have some problems. One reason is that contraction phases can make anisotropies, differences in the structure of the universe that go in different directions, so strong that they control the dynamics, which could stop a smooth bounce. Some models try to explain this by using strange types of matter or energy that weaken anisotropies when they fall. One more problem is entropy. According to the second rule of thermodynamics, disorder always grows. This means that in a world that bounces around, each cycle could take on more entropy than the last. If nothing is done, that increase could stop future bounces unless entropy is reduced or thrown away. Despite these challenges, the bounce concept remains compelling because it transforms the ultimate catastrophe into a new beginning. In this framework, the Big Bang we experience is not the unique birth of space and time, but simply the latest bounce in an eternal chain. If true, it means there was a universe before ours, and there will be one after it. Some bounce models predict that faint memories of the previous universe could survive the transition. These could be imprinted as tiny anomalies in the CMB, as relic particles older than our own expansion, or as subtle patterns in the distribution of galaxies. In other words, the evidence for a pre-Big Bang universe might already be hidden in the data, waiting for us to recognize it. Ekpyrotic universe mechanics. There are many ideas that try to explain what could lead to a second Big Bang. The Ekpyrotic model is one of the most brave ones. It changes more than just the history of our world, it changes the scene it plays on as well. From this point of view, the universe is not the only thing that exists. Instead, it's a brane, with 3 dimensions that floats in space with more dimensions. It's not alone. There is an unseen brane that runs parallel to ours and is linked to it by gravity. Every once in a while, the 2 branes crash into each other. When they do, they release so much energy that it starts something that looks and sounds like a Big Bang. This thought comes from string theory, which naturally says that there are more than the 3 dimensions of space and time. The bulk dimension is the only one that separates our brane from its parallel neighbor in the Ekpyrotic framework. The rest of the dimensions are very close together. The branes can move through this mass, and they can change directions at any time. Over periods that are hard to understand, they move toward each other. When the branes finally meet, Their collision releases colossal energy across their entire surfaces. The impact heats both brains to extreme temperatures, flooding them with radiation and matter. In our brain, the one we inhabit, it looks like a universe suddenly springing into being. Space begins expanding, matter forms, and over billions of years, stars, galaxies, and planets emerge. From inside, there's no sign of the other brain or the higher dimensional bulk. We only see the aftermath of the collision. The fact that the Ekpyrotic model easily fits into a cyclic structure is one of its most interesting traits. When two brains hit each other, they bounce back and start to move apart again. The phase of growth we're in now is part of this comeback. But at some point, gravity will slow down their movement apart, then reverse it and make the brains move back toward each other. The next crash will be like the Big Bang. It will be the start of the next cycle. The model also tries to answer some of the same questions that inflation theory was made to answer. In the case of the cosmic microwave background, which is almost the same temperature in all directions, this explains why the universe is smooth on a big scale. The long, slow contraction phase before a crash smooths out any bumps in space-time in the Ekpyrotic picture. Before the brains hit each other, the universe is already in a uniform state, so the expansion begins on an even playing field. There's also an advantage when it comes to avoiding singularities. In the standard Big Bang model, rolling the clock backward leads to a singularity of infinite density and zero size. But in the Ekpyrotic model, the collision happens when the brains are still finite in size and separation. The bulk space provides a buffer that prevents densities from going truly infinite, replacing the singularity with a violent but finite energy spike. Testing a theory based on invisible extra dimensions is, unsurprisingly, difficult. But the Ekpyrotic model does make predictions that could, in principle, be checked. One is in the spectrum of primordial gravitational waves, the ripples in space-time generated by the collision. Inflation predicts a specific distribution of gravitational wave strengths across different frequencies. The Ekpyrotic scenario predicts a much weaker spectrum, possibly even undetectable with current instruments. If future gravitational wave observatories fail to see the inflationary signal, that absence could be a point in the Ekpyrotic model's favor. Another possible clue lies in the details of the cosmic microwave background. Certain subtle patterns in its temperature and polarization maps might hint at the kind of pre-collision contraction the Ekpyrotic theory describes. Large-scale structure surveys, maps of galaxy distributions across billions of light-years, could also contain statistical fingerprints of a slow, smoothing contraction phase before our expansion began. The elegance of the Ekpyrotic model is that it takes concepts from high-energy physics, extra-dimensional geometry, and cosmology, and weaves them into a coherent story of cosmic renewal. It doesn't require the universe to be born from nothing. It doesn't require space and time to have a single origin point. Instead, it suggests our cosmos is part of a grander, multidimensional choreography, one that may have been repeating forever. The mechanism for brain motion in the bulk is still theoretical, and its stability over countless cycles is not guaranteed. Energy loss during collisions, the role of dark energy in brain dynamics, and the fine-tuning of initial brain conditions are all open questions. Still, these are the kinds of challenges that can drive theory forward, refining the model and pushing it toward predictions that can be tested. Quantum loop gravity predictions. As per normal general relativity, the beginning and possible end of the universe are controlled by singularities. These are places where density and curvature are endless and the physical equations stop working. But numbers that go on forever are usually a sign that a theory has hit the end of what it can explain. Loop quantum cosmology, LQC, which is a branch of quantum loop gravity, QLG, gives us a way to get past that edge. It doesn't predict singularities, but bounces instead. Bounces are times when the quantum features of space-time itself stop the crushing fall of space and turn it around. A big change in how we think about space and time is at the heart of quantum loop gravity. The universe is not smooth and continuous. Instead, it is made up of separate geometric atoms that are linked together in a network of loops at the Planck scale, which is equal to 10^3 meters. There is no space inside these rings. They are space themselves. Quantization means that distances, areas, and sizes come in units that can't be split up, like the energy levels in an atom. This granularity of space-time changes everything when it comes to extreme conditions, like those near a singularity. In a collapsing universe, densities and curvatures rise until they reach the Planck scale, where quantum geometry effects become dominant. Instead of allowing the collapse to continue unchecked, the quantized geometry produces an enormous repulsive force. This isn't a new form of matter or energy. It's a direct consequence of the way gravity behaves when space-time is fundamentally discrete. In loop quantum cosmology models, the equations of general relativity are modified to include these quantum corrections. When the density of the universe approaches a critical value, typically just below the Planck density, the sign of gravity's effect flips. Instead of pulling everything inward, gravity's quantum counterpart pushes outward. This repulsion becomes stronger than the contraction, forcing the collapse to stop and reversing it into expansion. The result is a bounce, replacing the singularity with a smooth, finite transition between contraction and expansion phases. This bounce isn't just a math trick to avoid infinities, which is what makes it so noticeable. It can lead to testable results. One theory says that the universe's early moments after the bounce might still have small traces of the universe before the bounce. The changing patterns of the cosmic microwave background, CMB, could carry weak echoes from before the bounce, which could be seen as strange things on the biggest angular scales. LQC also predicts modifications to the spectrum of primordial gravitational waves. In the inflationary picture, these waves are generated by quantum fluctuations stretched to cosmic scales. But in the bounce scenario, gravitational waves can also be generated during the contraction phase and transmitted through the bounce. The result could be a distinctive suppression of certain wavelengths, a signal that could be sought in next-generation observatories like LISA or CMB-S4. The idea that the bounce sets a maximum density for the universe is another important forecast. In the standard model of physics, there is nothing stopping density from growing as you get closer to the singularity. In LQC, the critical density is fixed and is usually thought to be 0.41 times the Planck density. This is a safety valve built into the rules of physics that keeps the universe from falling apart at a point where it curves infinity. The bounce structure changes the way we think about time as an arrow as well. Time starts at the Big Bang in a world based on singularities. It doesn't mean anything before that. In loop quantum physics, time keeps going after the bounce. The time arrow in the universe before the bounce points toward the bounce, but the time arrow in our universe points away from it. The bounce connects two different times in the past of the universe. One of the nice things about LQC is that it doesn't need any crazy new particles or types of matter to keep a singularity from happening. If you apply quantum physics to the gravitational field, the bounce will happen automatically. In this way, it is theoretically simple, but the math is anything but easy. It uses advanced methods from quantum geometry, spin networks, and Ashtekar variables to explain how space-time changes when things get really bad. But LQC does have some problems. One problem is making a smooth link between the bounce dynamics and the way the universe usually evolves. As we can see, the universe must go through processes like nucleosynthesis, warming, and structure creation after the bounce. Models are still being improved to make sure they fit perfectly with factors that have been measured in space. It can also be hard to tell the difference between bounce signatures and inflation signatures. In many cases, an inflationary phase comes after a bounce. This is what makes the world orderly and structured as we see it now. Inflation can hide or wash out pre-bounce signs, making it hard to tell the difference between the two in the data. So scientists are looking at small changes in the CMB's polarization patterns, and certain gravitational wave frequency bands as possible ways to tell them apart. Entropy reset challenges. There is one problem that can't be ignored if there is a second Big Bang in the universe: entropy. Entropy is a measure of disorder in thermodynamics. It is the number of tiny ways a system can be put together without changing how it looks overall. But in astronomy, it means a lot more than what it says in school. It is said that entropy is the arrow of time. It's why eggs don't crack again, smoke doesn't come back together in a cigarette, and the past and the future feel different. The second law of thermodynamics tells us that in an isolated system, entropy never decreases. The universe, as far as we can tell, is the ultimate isolated system. This means its total entropy has been steadily climbing since the Big Bang. Every star that burns its fuel, every black hole that swallows matter, every supernova that scatters heavy elements into space, all of it increases the overall disorder. That's not necessarily bad for life and complexity, but it poses a serious problem for any theory of cosmic rebirth. If a second Big Bang were to occur in the far future, it would somehow need to begin with a universe in an extraordinarily low entropy state, just like our first Big Bang did. Low entropy is essential for a smooth, uniform early cosmos, the kind that allows gravity to amplify tiny density fluctuations into galaxies and stars. But here's the catch. After trillions of years of evolution, our universe will be far from low entropy. In a heat-death scenario, matter will be thinly spread, stars will have burned out, and black holes will dominate, objects with entropy levels so high they dwarf everything else. In fact, the entropy of a single supermassive black hole can exceed the entropy of all the ordinary matter in the visible universe combined. According to the Bekenstein-Hawking formula, the entropy of a black hole is proportional to the area of its event horizon, not its volume. That means the bigger the black hole, the more entropy it contains, and the more formidable the challenge of resetting the universe's thermodynamic clock. The challenge grows when you realize that black holes themselves don't last forever. Over incredibly long timescales, up to 10 to the 99th years for the largest ones, they slowly lose mass through Hawking radiation. But this evaporation doesn't lower the universe's entropy, it just redistributes it. The emitted radiation is extremely high in entropy, which means it adds even more disorder to the cosmos. By the time the final black hole is gone, the universe will be saturated with entropy, spread evenly throughout space. In a cyclic or bouncing universe, this high entropy end state would be the starting point for the next cycle, unless there's a mechanism to reduce it. Without such a mechanism, each new cycle would start with more entropy than the last, eventually making meaningful structure impossible. This is sometimes called the entropy buildup problem, and it's one of the hardest hurdles for any cyclic cosmology to clear. Some theory models try to get around the problem by making entropy less strong during the growth phase. In situations with extra dimensions, for example, entropy could be leaked into the mass with higher dimensions. This would clean up our three-dimensional brain for the next contraction. Others say that entropy might be swept away into parts of space that are beyond our ability to observe. This would remove it from the part of the universe that will be involved in the next bounce. Another way is to have a period of fast growth followed by a period of slow growth. This is like inflation, but the opposite of it. Space would be stretched so quickly during this deflation phase that any entropy would be reduced to almost nothing compared to the total volume. But a phase like this might not be possible if dark energy behaves in a way that we don't understand, and if it can undo its effects in the right way, at the right time. The Ekpyrotic model offers a partial workaround. In its slow, smoothing contraction phase, irregularities in density and curvature are dampened out. While this can create a more uniform starting point for the next expansion, it doesn't fully eliminate the entropy already embedded in black holes and radiation. Those components still have to be dealt with, and the theory doesn't yet have a complete answer. Some of the worst singularity problems can be avoided with quantum gravity methods, such as loop quantum cosmology, However, the entropy problem still needs to be solved. Even if the bounce goes easily, the high entropy universe before the bounce has to be balanced with the low entropy conditions needed for structure formation after the bounce. Some experts think that quantum effects close to the bounce might be able to scramble information in a way that restarts entropy, but this is still just a guess and would be hard to prove mathematically. There's also the bigger question of why the entropy was so low at the start of the Big Bang. Roger Penrose has said that the universe was in a very unique state at the start, with a lot more order than most possible arrangements of the same amount of energy. If there is to be a second Big Bang, it needs to make a similar unique state, but we still don't know how the first one did it. The idea of a reset could become more of a hopeful assumption than a well-thought-out prediction without a clear way to make it happen. The holographic principle in cyclic models. If the world does go through cycles of huge periods of growth, breakdown, and rebirth, then there is only one question that can be asked. What happens to all the information during each cycle? When a new world starts, do the events of the old one disappear forever, or is there a way for information to stay alive? Our unexpected answer comes from the hologram principle. Nothing is ever really lost in the deep structure of space-time. The holographic principle began as an insight from black hole physics. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy, and that this entropy is proportional not to their volume, but to the area of their event horizon. This was strange. It implied that all the information about the matter inside a black hole could be represented on a two-dimensional surface surrounding it, like data stored on a holographic plate. In the 1990s, Gerard 't Hooft and Leonard Susskind extended this idea beyond black holes, proposing that the same principle could apply to the universe as a whole. In this view, the three-dimensional world we experience could be a projection of information encoded on a two-dimensional boundary far away, possibly at the cosmic horizon. Just as a hologram contains all the information about a 3D image in a flat surface, the cosmos could contain all the information about its contents in a 2D framework. In cyclic universe models, this concept opens an intriguing possibility. If the universe ends in a contraction or a bounce, the information about everything that happened, every galaxy that formed, every black hole that evaporated, might be stored not in the matter itself, but in this holographic encoding. That means when the next cycle begins, the initial conditions could still be influenced by the data from the previous one. How this might work depends on the underlying geometry of the bounce. In a brane collision scenario, for instance, the information could be preserved on the higher dimensional bulk boundary between branes. In a loop quantum cosmology bounce, it could be stored in the quantum state of the space-time network itself, carried through the moment of maximum compression without being erased. Either way, the holographic framework offers a mechanism for information continuity that doesn't rely on matter or radiation surviving the transition in the conventional sense. This has very important implications for physics. In the old way of thinking about physics, black holes seemed to threaten to destroy information. Anything that crossed their boundaries was thought to be lost forever. But if the hologram principle is right, data doesn't get lost in black holes. It just gets spread out across the sky in a very jumbled way. In the same way, the horizon of a universe that is falling could be the same for all the information in that universe, whether it's a brane surface or a quantum statistical limit. The information could be jumbled, but it wouldn't be lost. This makes the idea of cosmic memory possible. If each cycle keeps some information about the one before it, then small patterns could be left on the structure of the new world. In theory, these could show up as statistical outliers in the cosmic microwave background, CMB, connections in the ways galaxies are spread out, or strange patterns in big cosmic structures. It would be very hard to find these kinds of fingerprints because the information would be jumbled and damaged by the bounce, but it might not be impossible. There are even physicists who think the holographic principle could help solve the entropy problem in circular models. In the event that all the chaos from a previous universe is stored in holograms, the new universe may begin physically fresh, but it may still hold a record of information at a lower level. This would avoid the thermodynamic growth of disorder while still following the rules for keeping information safe. This is still very much a guess, though, and would need a much more complete theory of quantum gravity to be proven. The hologram concept is already being put to the test. The ADES-CFT correspondence is one of the most likely ways to do this. It is a mathematical duality between a gravitational theory in a higher dimensional space, like the space between branes, and a quantum field theory that doesn't have gravity on its border in a lower dimensional space. In idealized worlds with negative curvature, this relationship is easiest to understand. However, it shows how holography can keep information safe and send it between different dimensions. In the context of cyclic cosmology, applying holography would mean treating the end of one universe and the birth of the next as two different views of the same underlying information state. The violent processes at the bounce wouldn't annihilate information. They would re-encode it into the starting conditions of the new cycle. This could mean that at some deep level, our universe still carries the fingerprints of universes that came before. Of course, not everyone agrees. Some people disagree with this idea because we don't fully understand how the holographic principle works in real-life cosmologies, especially ones with bounces, expansions, and contractions. The idea came from studying string theory and black holes. Applying it to the whole universe is a big step that hasn't been proven yet. Also, just because holography keeps data safe doesn't mean it will be usable or recognizable in the next cycle. Vacuum decay and false vacuum instability. Quantum field theory says that stability can be misleading, even though our world seems to be steady. Though we call it empty space, it's not really empty. It's full of fields, with the Higgs field being the most important. It is the Higgs field that gives particles their mass and forms the rules of physics, but its value may change over time. There's a chance that the Higgs field, and by extension, the structure of our universe is only metastable right now, a false vacuum sitting in an energy valley that isn't the deepest one that's available. In this case, the real vacuum, which is the state with the least amount of energy, is outside of a quantum boundary. The universe can stay in the fake vacuum for billions or even trillions of years if everything is normal. But quantum physics allows a rare event called quantum tunneling to happen. This is when the field leaps through the barrier and sinks into the real vacuum. This event would start a bubble of pure vacuum that grows at almost the speed of light, changing the rules of physics as it goes. The transition from false to true vacuum is catastrophic in its implications. The constants of nature, the speed of light, the masses of particles, the strengths of forces, could all change inside the true vacuum bubble. Chemistry as we know it would break down instantly. Atoms might not form. Stars, planets, and life itself would have no chance to adapt. And because the bubble wall would travel at light speed, no signal could warn us. By the time it arrived, we would already be inside it. From a cosmological standpoint, however, such an event could be more than just an end. A true vacuum might have a radically different energy density than our current false vacuum, and this could drive an explosive expansion similar to inflation. In effect, a vacuum decay could serve as the spark for a new cosmic era, the first moment of a second Big Bang unfolding under completely new physical laws. The question of whether our universe is in a false vacuum is tied to the properties of the Higgs boson, discovered at CERN in 2012. Current measurements of the Higgs mass and the top quark mass suggest that we may be near the edge of stability. The calculations, based on the standard model of particle physics, place us in a gray zone where the Higgs potential is shallow enough to allow tunneling, but with a timescale far longer than the current age of the universe. This means the danger is theoretical, not imminent, but it also means the door is open for such an event to happen eventually. In principle, vacuum decay could also be triggered by extreme events. High-energy particle collisions, whether in the early universe or near the horizons of evaporating black holes, could push the Higgs field over the barrier. Even cosmic ray collisions at energies far beyond human technology might act as seeds for a true vacuum bubble. While no known natural process today is likely to cause this, the history of the universe is full of unknowns, and the possibility cannot be completely ruled out. From the perspective of quantum field theory, vacuum decay is an example of a phase transition, similar in spirit to water freezing into ice or boiling into steam. Except here, the substance is the vacuum itself, and the consequences are cosmically final. In inflationary cosmology, it's believed that different regions of space could be in different vacuum states, a concept known as eternal inflation. In this framework, our observable universe might just be a patch of false vacuum, surrounded by other regions already in true vacuum states. If so, the transition could be happening elsewhere in the cosmic expanse right now. A vacuum collapse could create a new expanding area, or new universe, inside the real vacuum bubble. This is one of the most interesting theories. From the inside, things would look and feel exactly the same as they did during the Big Bang. Rapid growth, the creation of new particles, and the building of cosmic structure. This would mean that vacuum decay is both the end of the universe and a possible way for new ones to start, maybe in a chain of universes that never ends. The challenges for this idea are significant. A transition to a true vacuum with very different physical constants could produce a universe inhospitable to complexity or life. If the Higgs potential's true minimum is too steep, the result could be a sterile, rapidly expanding space with no matter or radiation at all. In that sense, vacuum decay might be more of a final erasure than a cosmic rebirth. Detecting signs of false vacuum instability is difficult. The Higgs potential is influenced by physics beyond the standard model. Things like supersymmetry, quantum gravity, or unknown high-energy interactions could alter the stability picture entirely. Until we have better measurements of fundamental parameters, we can't know for certain whether the vacuum is absolutely stable, metastable, or unstable. At this point, we can only talk about probabilities. Many experts think that our false vacuum will last a very, very long time, much longer than the age of the universe. This is because vacuum decay is real, and there is no new physics beyond the standard model. What's important to remember is that even if the normal lifespan is incredibly long, it's still not endless. Rare things do happen in an endless stretch of space and time. In other words, the odds are always very small, but they are never completely zero. Inflationary potentials and scalar fields. A second Big Bang would need more than just a huge amount of energy to be released. It would also need a way to turn that energy into a world that is growing very quickly. In modern astronomy, that process is called inflation. Inflation was a time of exponential growth in the early universe that made space much bigger in a very short amount of time. The scalar field is a mystery part of inflation that makes it work. A scalar field is a quantity defined at every point in space and time, described by a single number rather than a direction. The Higgs field is one example, but in inflationary theory, the relevant field is hypothetical, often called the inflaton. Its behavior is determined by its potential, a kind of energy landscape that dictates how the field evolves. The shape of this potential is everything. If the potential is flat over some region, the inflaton can roll slowly across it, allowing inflation to last long enough to produce the smooth, uniform cosmos we observe. A steep potential, on the other hand, would cause the field to roll quickly, cutting inflation short. The precise slope and curvature of the potential control not only the duration of inflation, but also the spectrum of density fluctuations imprinted on the universe, fluctuations that later grow into galaxies and clusters. For a second Big Bang scenario, the conditions would need to reset in such a way that a scalar field finds itself perched high enough on its potential to drive rapid expansion again. This could happen in several ways. In a cyclic model, the collapse or bounce of a previous universe might kick the scalar field into a high-energy configuration. In a brane collision model, the collision could inject energy directly into the field. In vacuum decay scenarios, the transition to a true vacuum could place the field at the top of a new potential, ready to roll. But starting inflation again isn't enough. It needs to happen in the right way. During inflation, changes in quantum mechanics are pushed to the huge sizes of the universe and become the building blocks of structure. What the statistical features of these changes are rely on how the potential is shaped. If there is a second inflationary phase, the universe might have very different big-picture patterns than the one we live in now. Things that can be seen, like the scalar spectral index and the tensor-to-scalar ratio, which are recorded in the cosmic microwave background, would show signs of the second inflation. There's also the matter of how much energy there is. It is likely that inflation in our universe happened at energies close to 10 giga-electronvolts, which is close to the grand unification scale. In theory, a second Big Bang could happen at a different size, based on how the scalar field moves and how much potential it has. If the size was smaller, the gravitational wave background would be weaker. If it were larger, it might be stronger, and future efforts like LISA or the Cosmic Explorer might be able to find it. That is hard to model because scalar field potentials can look like simple parabolas, plateaus, sharp hills, or landscapes with many branches and multiple minima. Without knowing the high-energy physics behind them, cosmologists have to look into a lot of different options because each form has a different effect on inflation. String theory, for instance, says that there are a huge number of different ways that scalar fields can be set up, and each one has its own potential and increasing behavior. Restarting inflation also raises the issue of reheating, the process that converts the inflaton's energy into the matter and radiation that fill the universe. In our Big Bang, reheating marked the end of inflation, flooding space with particles that would eventually form stars and galaxies. For a second Big Bang, reheating would need to occur efficiently to produce a universe capable of complexity. If the energy stayed locked in the scalar field for too long, the resulting cosmos might be cold, empty, and lifeless. Eternal inflation is another thing to think about. There are times when quantum fluctuations can make the inflaton roll uphill as well as downhill. This creates a hybrid universe where inflation never ends in any one place at the same time. This process keeps making new areas of space and could go on forever. A second Big Bang could start inflation all over again in this kind of environment, but it might not create a single unified universe. Instead, it could create another branch of a huge growing multiverse. It is hard but not impossible to test the role of scalar fields in a made-up second Big Bang. There are hints about the inflationary potential in the cosmic microwave background, in the way galaxies are spread out, and in the range of primordial gravity waves. If we could find a bounce or transition signature, something that our first inflationary phase can't explain, it could lead us to a previous cycle and a scalar field that is once again active. Pre-Big Bang string theory models. Classical general relativity says that the Big Bang is the final limit. It is a single point where densities, temps, and curvatures are all infinite and the word before has no meaning. With its extra dimensions and long objects, string theory, on the other hand, offers a math sandbox where this hard limit can be loosened up. Some ideas say that the Big Bang is not the very beginning, but rather a transitional event that connects the pre-Big Bang phase to the hot growing world we live in now. String theory changes how we think about spacetime by replacing point-like particles with tiny vibrating strings that have a definite size, about the Planck length, or 10 to the minus 35th meters. Because these strings aren't infinitely small, they can smooth out the mathematical infinities that appear in traditional particle physics. The theory also brings in new symmetries, like T-duality, which connects very large and very small dimensions in unexpected ways. In T-duality, a universe that's compacted to an incredibly tiny radius can be mathematically the same as one that's huge. This means that shrinking and expanding could actually be two different views of the same physical reality. In the pre-Big Bang scenario, developed in the 1990s by Gabriele Veneziano and others, the universe begins in a cold, empty, and weakly coupled state far in the past. Driven by the dynamics of the dilaton, a scalar field unique to string theory, The cosmos contracts in the Einstein frame but expands in the so-called string frame. As the dilaton increases, the string coupling grows stronger and the curvature of space-time increases. Eventually, the universe reaches a high curvature, strong coupling regime where classical descriptions fail and quantum string effects dominate. This regime plays the role of the Big Bang in standard cosmology, but instead of a singularity, it's a smooth but intense transition into the hot, dense state of the early universe. The unity of the pre-Big Bang model is one of its most interesting features. The formulae that govern the pre-Big Bang phase are the same ones that govern the post-Big Bang phase. This means that the past of the universe is time-symmetric around the transition, with a branch that contracts due to dilaton forces before and a branch that expands due to radiation forces after. This symmetry goes against the usual idea of an arrow of time, which means there could be a world with a clear before. String theory sees the universe's starting conditions as general. They don't need to be set by hand. They just happen when it starts out in a low curvature, weakly coupled state. Over time, the gravity and dilaton fields make quantum changes stronger. This could create the building blocks for structure that later grow into galaxies and clusters. The pre-Big Bang method, on the other hand, doesn't need a specific inflaton potential. Instead, it uses the dilaton and other string fields to drive its early growth. The transition between the pre- and post-Big Bang phases, often called the graceful exit problem, remains a significant challenge. For the model to be viable, the high curvature phase must connect smoothly to the standard hot Big Bang phase without producing excessive inhomogeneities or violating observational constraints, such as the uniformity of the cosmic microwave background, CMB. Various proposals involve higher-order string corrections, brane interactions, or new physics that become relevant at strong coupling. Another avenue comes from brane cosmology, an offshoot of string theory, where our universe is a three-dimensional brane embedded in a higher dimensional bulk. In these models, the Big Bang can be reinterpreted as the result of a collision between branes. Before the collision, the branes move through the bulk, possibly containing their own evolving universes. The moment of impact transfers energy into the branes, heating them and creating the conditions for a hot, dense universe. This picture naturally accommodates a before without requiring a singularity, and it provides a geometric mechanism for cosmic resets in cyclic scenarios. Pre-Big Bang string models also have testable consequences, at least in principle. The dynamics of the dilaton and the high curvature transition could leave distinctive imprints on the spectrum of primordial gravitational waves. In particular, some versions predict a blue-tilted spectrum, more power at high frequencies, in contrast to the red-tilted spectrum expected from standard inflation. Future gravitational wave observatories, sensitive to frequencies far above those probed by CMB polarization, could search for this signature. Another possible signal lies in primordial magnetic fields. The rapid changes in the dilaton and the geometry during the pre-Big Bang phase can generate seed magnetic fields, which might later be amplified to the strengths observed in galaxies today. Detecting the properties of such fields could offer indirect evidence for a pre-Big Bang origin. Some people who don't like the pre-Big Bang model say that it doesn't have some of the best features of inflation, like being able to easily explain why the universe is flat and isotropic. It's harder to get rid of remnants or make the universe more uniform without a time of fast growth after the transition. But hybrid models that combine parts of both inflation and pre-Big Bang dynamics have been suggested. These models give the best of both while keeping the idea that the universe has a past. Because string theory is so mathematically rich, it can also be changed in more unusual ways. In some cases, the universe before the Big Bang might have had extra dimensions when it was big and not compressed. These dimensions may have later curled up into the tiny shapes we can't see now. In some cases, the past might include changes in the topology of spacetime, with different areas going through different geometric changes before coming together in a single post-Big Bang age. All of these versions have one thing in common. The Big Bang is no longer seen as an absolute end to time. Instead, the bang turns into a bridge, a high-energy doorway that connects two eras. The math behind strings and brains makes sure that the story of spacetime goes on forever in both ways. Cosmic contraction dynamics. In order for any cycle or bounce model to work, the universe must first stop expanding faster before it can have a second Big Bang. In order for this to happen, there must be certain gravity conditions that can counteract the pulling force of dark energy and move all matter and radiation back toward a state of high density. To figure out how such a change could happen, we need to look closely at how the universe's energy, structure, and fundamental forces interact with each other. In general relativity, the expansion or contraction of the universe is governed by the Friedmann equations. These equations link the rate of expansion to the density of matter and energy, the curvature of space, and the cosmological constant. For expansion to halt and reverse, the total energy density must reach a point where gravitational attraction dominates over any repulsive effects. In a universe like ours, where dark energy currently accounts for roughly 70% of the total, this is not the natural trajectory. Dark energy's negative pressure drives accelerated expansion, making contraction impossible unless its properties change dramatically. It is thought that the dark energy's equation of state constant, W, could change over time, which could lead to shrinkage. Dark energy might stop repelling things if W goes above -1 and turns positive. It would then act more like normal matter or radiation. Scalar field dynamics, which models dark energy as a slowly moving field that changes its behavior over time, could cause this shift. Dark energy could also break down into matter or radiation, making it less powerful and letting gravity pull everything back together. Adding new gravity physics on top of Einstein's theory is another option. Different types of gravity models, like FR gravity or huge gravity, can create situations where growth naturally slows down and turns around in some situations. Higher order curvature terms or more degrees of freedom in the gravity field change the formula for how the universe evolved. This makes a way for the universe to get smaller without dark energy having to change what it is. Matter density also plays a critical role. In the early universe, when matter density was much higher, gravity easily overcame expansion on small scales. To reproduce contraction on a cosmic scale, the average density would have to increase again, something that could happen if the universe were finite in size, and matter was recycled through black hole evaporation or other exotic processes. In a closed universe with positive curvature, the geometry itself contributes an inward pull, making contraction more likely. However, current observations suggest the universe is flat or nearly flat, so curvature alone is unlikely to drive the reversal. The start of decline would not be the same slowing down of growth everywhere. Structure creation, gravitational grouping, and local inhomogeneities could all have an effect on the process, making some areas collapse faster than others. Over the course of cosmic time, these areas might join together, which would cause a bigger fall. Some cyclic models say that contraction starts at the biggest sizes and moves down to smaller ones. This means that galaxy superclusters are pulled closer together before smaller structures are affected. As contraction progresses, the universe's temperature and density rise. Radiation becomes increasingly important, eventually dominating over matter. The approach to a bounce, if one occurs, depends on what happens at extreme densities. Classical general relativity predicts a singularity, but quantum gravity effects could modify this, producing a rebound instead of a final collapse. Matter-antimatter asymmetry in a second bang. Why there is so much more matter in the world than antimatter is one of the biggest puzzles in cosmology. The known rules of physics say that the Big Bang should have made the same amount of matter and antimatter. But when the original plasma cooled, almost all of the antimatter and its matter partners were destroyed. There was only a tiny bit of extra matter left over, 1 part in 10 billion, that turned into everything we see today. This mismatch is known as baryon asymmetry, and it only happened under certain conditions in the very beginning of the world. If the universe were to undergo a second Big Bang, whether through a bounce, a brane collision, or a vacuum decay, the entire process of baryogenesis could, in principle, happen again. The question is whether it would produce the same imbalance we see today, a different one, or none at all. Baryogenesis relies on 3 key conditions, first outlined by Andrei Sakharov in 1967: baryon number violation, C and CP symmetry violation, and a departure from thermal equilibrium. In the standard model, CP violation, a difference in the behavior of matter and antimatter, exists, but not at a level sufficient to explain the observed asymmetry. This suggests that new physics, such as interactions involving heavy particles beyond the standard model, played a role in the early universe. In a second bang, the reset conditions would depend on the energy scale of the event. If the new universe reached similar or higher temperatures than the first, it could create the same types of heavy particles, such as hypothetical right-handed neutrinos, whose decays generate the necessary CP violation. This process, called leptogenesis, could seed the baryon asymmetry by first creating an imbalance in leptons, which is then converted into a baryon imbalance through electroweak interactions. If the second bang had a different inflationary or reheating phase, the particle content could be entirely different. Different scalar fields could dominate reheating, leading to altered decay channels and CP-violating processes. The result could be a matter-antimatter ratio distinct from our own, potentially higher, lower, or even reversed. In the extreme case where the asymmetry favored antimatter, the large-scale structure of the new universe could look much the same, but all chemistry and biology would be built from antimatter. The microphysics of a second baryogenesis event also depend on the cosmological timeline leading up to it. In cyclic models, residual asymmetries from the previous cycle might persist in some form. If certain particles survive the bounce, such as long-lived dark sector particles with baryon-like properties, they could bias the baryogenesis process in the next cycle. In contrast, if the bounce or reset is violent enough to destroy all pre-existing particles and fields, the asymmetry would have to be generated from scratch. Even worse things happen in situations where vacuum rot happens. When a false vacuum turns into a real vacuum, it can change the basic laws and patterns of nature in big ways. If that's the case, the CP-violating events that made baryogenesis possible in our universe might not even be there in the new one. If this is the case, whether matter rules or not would rest only on the particle physics of the true void. Observationally, it's hard to understand baryogenesis in a second bang, because the only direct proof we have for our own baryon asymmetry comes from the fact that the universe doesn't have a lot of annihilation radiation, and the elemental abundances suggested by Big Bang nucleosynthesis. Some things that might have been left over from the first cycle, like unevenities in the gravity wave background or strange geometric flaws, could affect the conditions in which baryogenesis happens in the second cycle. The idea that matter-antimatter asymmetry could reset also has deep implications for cosmic habitability. A universe with a much smaller asymmetry might have too little matter to form complex structures after the majority annihilated. A universe with a much larger asymmetry might form structures faster, potentially leading to denser galaxies and a different astrophysical landscape. In either case, the balance between matter and antimatter after a second bang would play a decisive role in shaping the cosmic environment. Baryogenesis is still one of the hardest problems in astronomy to solve, and a second Big Bang scenario wouldn't help, but it would give us a new point of view. We could ask if the imbalance we see is a one-time event during the birth of our universe, or a common feature of cosmic restarts. Primordial gravitational waves from previous cycles. Gravitational waves are changes in the fabric of space-time that happen when heavy things move faster than expected in one direction. In contrast to electromagnetic radiation, they have very weak interactions with matter. This means that they have been able to move through the world almost unchanged since they were created. Because of this, they are perfect messengers of the past. In a world that cycles or bounces, they could carry knowledge about things that happened before the Big Bang. Standard cosmology says that the first gravitational waves were likely made during the inflationary phase, when quantum changes in the gravitational field were stretched to cosmic sizes. All space would be marked by this background signal, which would be weak but present everywhere. In a circular model, similar waves could have been made not only during our current inflationary phase, but also in earlier ones. They might have survived the bounce between cycles and come into our universe as leftovers from a different time in the universe's history. The survival of such signals depends heavily on the physics of the bounce. In a purely classical collapse, space-time curvature would grow without bound as the universe contracts, leading to a singularity where all information is lost. But in models where quantum gravity effects replace the singularity with a smooth bounce, as in loop quantum cosmology or certain string theory scenarios, gravitational waves can pass through, albeit with their amplitudes and frequencies modified by the extreme conditions of the transition. If these waves did survive, their spectrum could be quite different from the one generated in our own cycle. For example, in a contracting phase dominated by stiff matter, where pressure greatly exceeds density, gravitational wave amplitudes grow rather than decay. This could amplify certain modes to observable levels today. The resulting background might have a blue-tilted spectrum, with more power at higher frequencies than inflationary models typically predict. Such a tilt could serve as a fingerprint of a pre-Big Bang origin. Finding these very old signs is a huge task. Gravitational wave monitors like LIGO, Virgo, and Kagra are meant to record short-lived events from astrophysical sources, such as neutron stars crashing into each other or black holes merging. These events happen at frequencies ranging from tens to thousands of hertz. Gravitational waves from past cycles could have very different frequencies, ranging from nanohertz to gigahertz, based on how the bounce and contraction happened. At the lowest frequencies, corresponding to wavelengths comparable to the size of the observable universe, these waves could leave an imprint on the polarization of the cosmic microwave background, CMB. Specifically, they would produce a distinctive B-mode polarization pattern, a curling twist in the orientation of the CMB's light. Experiments like the Simons Observatory and CMB-S4 aim to push the sensitivity of polarization measurements to the level needed to detect such a signal. If a blue-tilted spectrum from a previous cycle exists, its high-frequency tail might also be accessible to next-generation detectors like LISA, Laser Interferometer Space Antenna, which will probe the millihertz range from space. When frequencies get much higher, recognition is less certain. In theory, proposed resonant detectors, optically levitated sensors, and electromagnetic cavity tests should be able to pick up gravity waves on the gigahertz scale. When the universe's curve radius is about the size of a micron, these rhythms might be the natural result of processes happening in the last few seconds before a bounce. Gravitational waves from previous cycles would not be accompanied by any electromagnetic counterpart. Their detection would therefore rely entirely on matching a measured spectrum to a theoretical model of pre-Big Bang dynamics. This requires disentangling them from the gravitational wave backgrounds generated by astrophysical sources in our own cycle, such as the combined hum of all binary systems throughout cosmic history. It would be the first straight look into the physics beyond the Big Bang singularity, something that can't be done with any other way of observation. The equation of state of the shrinking universe, the length and type of the bounce, and even the presence of extra dimensions could be found in the wave spectrum if it showed signs of modes leaking into or out of space with more dimensions. It's also possible that the spectrum has sharp features like resonances or cutoffs that match certain events that happened before our universe was formed. These could be brain collisions, phase changes in exotic fields, or even the disappearance of black holes that formed in a previous cycle. Each would add a new level of structure to the background, making it not only a proof of cyclicity, but also a record of history from before the Big Bang. Dark energy phase transitions, sudden shifts in the cosmic acceleration. When people talk about dark energy, they usually think of it as a smooth, constant force that stretches the world over billions of years. But in more complicated models, dark energy might not be steady at all. Instead, it might go through sudden phase changes that flip its traits in a way that could completely change cosmic development in a very short amount of time. In physics, a phase transition is what happens when a system changes state, water freezing into ice, or iron becoming magnetized. The same idea applies in quantum field theory. A field can move from one configuration to another, releasing or absorbing energy in the process. If dark energy is driven by a scalar field, its potential energy landscape might contain multiple valleys, each corresponding to a different vacuum state. The universe could linger in one valley for eons, only to suddenly tunnel or roll into another. If such a shift occurs, the equation of state for dark energy, the ratio of its pressure to its energy density, could change abruptly. This wouldn't just alter the rate of cosmic acceleration, it could reverse it entirely. A universe coasting along in accelerated expansion might find itself suddenly decelerating, and if conditions allow, tipping into contraction. That contraction could then set the stage for a high-density rebound, a second Big Bang. A change could send acceleration into gear, pushing the universe toward an uncontrollable expansion. In some situations, the quantity of dark energy could rise, causing effects like a little rip, in which structures break apart slowly without an immediate singularity. In some cases, the shift could be like a short, powerful wave of inflation, stretching space-time a lot before it settles into a new state. The particle physics would determine when and how big these changes would be. It is possible for a slow shift in the scalar field to bring it close to a cliff in its potential, which would cause a rapid drop. In models based on string theory, different light fields could combine in ways that sometimes let energy stored in them escape into the empty space. Quantum tunneling might also make it possible for the field to move from a false vacuum to a real one in some metastable vacuum models. It would be very hard to tell when such a shift is about to happen. The way the growth rate changes over time, on the other hand, could show small signs. Surveys that will soon be done by Euclid, the Nancy Grace Roman Space Telescope, and the Vera C. Rubin Observatory might find acceleration that isn't smooth, especially if the equation of state starts to move quickly. Other signs could show up in the rate at which large-scale structures grow, in the combined Sachs-Wolf effect in the CMB, or even in the speed at which gravity waves travel over very long distances in the universe. Phantom energy and the Big Rip pathway. Out of all the possible endings for the universe, the Big Rip is the most violent. It is caused by phantom energy, which is a very strong form of dark energy. The equation of state quantity W is less than -1 in this case. This means that dark energy has a pressure that is even lower than a cosmic constant. This leads to uncontrollable speeding up. The more the universe expands, the heavier the phantom energy gets, which speeds up growth even more in a feedback loop that ends with total destruction. In most versions of dark energy, the quantity of energy stays the same or goes down as the universe grows. This rule is broken by phantom energy. Its gravitationally repelling effect gets stronger over time instead of weakening because its density grows with the scale factor. When this happens, a clock starts to tick. It's not counting down to a slow, cold death, but to a point in the future where time stops. The scale factor goes to infinity, space-time curves split, and the known laws of physics don't work anymore. The sequence leading to the Big Rip can be calculated once W and the current dark energy density are known. Long before the final moment, the acceleration rate becomes so high that it begins to overwhelm all binding forces in the cosmos. First, galaxy clusters lose their gravitational grip, with their members receding faster than gravity can hold them together. Billions of years later, galaxies themselves disintegrate, their stars drifting apart into the deepening void. As the timeline advances toward the final millions of years, phantom energy stretches even stellar systems beyond their limits. Planetary orbits destabilize, with worlds cast adrift from their parent stars. In the last minutes, the effect reaches the scale of individual planets and moons, tearing them apart as the tidal forces from space-time expansion outmatch their internal binding. In the final fraction of a second before the rip, even atoms cannot survive. Electrons are ripped from nuclei, and the most fundamental particles are driven apart as space itself races toward infinite expansion speed. The time left before a possible big rip depends a lot on how far W is below -1. If it is just a little lower, about -1.01, the universe could last for tens of billions of years. But if it drops to -1.1 or less, the end could come in only a few billion years. That is not much longer than the universe has already been around. This makes phantom energy models both scary and hard to measure, because even tiny errors in W lead to huge errors in predicting when the universe might rip itself apart. Phantom energy is strange because it goes against the null energy condition, which is a basic idea used in many general relativity proofs and theories. If this condition is broken, strange things can happen, like the scale factor expanding faster than light, wormholes becoming unstable, and even the possible chance of strange matter being created from the vacuum. Even though these ideas are still just guesses, they show how far away phantom energy is from normal cosmic physics. If phantom energy truly governs the universe's fate, there's no natural mechanism for a second Big Bang in the traditional sense. The approach to the rip leaves no contracting phase or bounce. Instead, all distances grow without bound until no coherent structures remain. However, some theorists have speculated that quantum gravity effects could intervene before the final singularity, potentially transforming the disintegration into a different kind of phase transition. In such models, the rip might serve as a bridge into a radically new regime of physics, one that could spawn a new expanding spacetime, perhaps with entirely different laws and constants. From what we can see, the idea of ghost energy is still open for discussion. The latest data from supernovae, baryon acoustic waves, and the cosmic microwave background all support the idea that W equal -1, but there are small differences that fall into the phantom range. To get the accuracy needed to say for sure whether it's true or not, we will need to do next-generation studies of the past, of cosmic expansion and structure growth. Modified gravity theories in rebirth scenarios. Einstein's general theory of relativity has been the basis of astronomy for more than 100 years. It has been used to accurately predict everything from how black holes will behave to how the universe will expand. But it has a flaw. In its normal form, it suggests singularities, which are places where the equations don't work because of infinite volumes and curves. It is hard to picture a smooth rebirth of the universe because of these singularities, which can be found both at the Big Bang and inside black holes. That's why some cosmologists use modified gravity theories, which change or add to Einstein's equations to get around these infinities and make reasonable ways for there to be a second Big Bang. FWR, gravity is one of the most studied methods. In this method, the Ricci scalar curvature R is changed in Einstein's equations to a more general function, RR. This change, which seems easy, lets spacetime act differently in very bad situations. In some types of FR gravity, the equations automatically cause cosmic bounces, which are contractions followed by expansions, without the need for strange matter that breaks the rules of energy. At high densities, the curve can act as a pushing force, stopping the fall into a singularity and making way for a new hot, dense phase like the Big Bang. Another contender is massive gravity, in which the graviton, the hypothetical quantum particle that mediates gravity, is given a small but non-zero mass. This changes how gravity operates over very large distances, and can influence the overall fate of the universe. In some massive gravity models, the late-time acceleration attributed to dark energy emerges naturally, and under certain parameter choices, the expansion can slow and reverse. The contraction phase can then feed into a bounce mechanism, possibly leading to cyclic behavior. The graviton's mass also affects the propagation of gravitational waves, potentially leaving imprints that could be searched for as evidence of previous cycles. There are also higher dimensional theories like brane-world gravity, where our observable universe is a three-dimensional brane embedded in a higher dimensional spacetime. In these scenarios, gravitational interactions can leak into the extra dimensions, modifying the standard Friedmann equations at both low and high energies. Some brane-world models predict that brane collisions in the higher dimensional bulk could periodically trigger new Big Bang-like events. Others allow the extra dimensions themselves to oscillate or evolve in ways that periodically reset the four-dimensional universe we inhabit. Changes that are inspired by loop quantum gravity also fall under this category, but they come from a very different reduction method. In this case, the discrete state of spacetime at the Planck scale changes the equations that describe how the universe moves, switching out singularities for bounce points. In traditional general relativity, the curvature can get bigger and bigger, but these models put a ceiling on the highest density and curvature. This makes sure that a universe that is collapsing will eventually start to expand again. These different methods to modify gravity all have one thing in common. They can all make a non-singular change from collapse to growth, which is an important part of any rebirth situation. As well as being flexible, they let you choose what causes a bounce. It could be geometric terms in the equations, new fields connected to gravity, or interactions with extra dimensions. The changes sometimes even make it possible for the universe to go through more than one cycle without having to fine-tune the starting conditions. Using observations to test these ideas looks like a good but difficult plan. Small changes in the rate at which cosmic structures grow, changes in gravitational lensing patterns, or strange things in the cosmic microwave background could all be signs of deviations from general relativity. There may be patterns that happen over and over again in repeated situations. For example, a chosen scale in changes in density or a unique gravitational wave background created by changing how gravity works. Thermalization. Timescales in a new universe. It doesn't matter if the universe started in the Big Bang or a made-up second one. It starts out very dense and very hot, but it's not always even, smooth, or ready to form the buildings we see today. Right after, things are a mess. Quantum fluctuations that are spread out across space, areas with different amounts of energy, and particle types that aren't balanced with each other. The process by which the universe changes from being very chaotic to being mostly regular and hot is very important for determining the starting points of cosmic growth. When the well-known rules of thermodynamics start to apply on a cosmic scale depends on how long this takes to happen. Thermalization happened very quickly by our standards in the past of our own world, but not right away. In the first few seconds after the Big Bang, there was so much energy in the space that particles were constantly colliding and being made. Matter, antimatter, and radiation interacted at speeds much faster than the growth of the universe. This kept the system's temperature stable in the area. In these conditions, all particle types had the same temperature, and the way their energies were spread out followed patterns explained by quantum statistics. For bosons, these patterns were Bose-Einstein, and for fermions, they were Fermi-Dirac. Equilibrium is not stable. Reaction rates slow down as the world gets bigger and cooler. Species separate from the thermal bath when the rate at which particles interact drops below the rate at which the universe is expanding. Different particles froze out at different times. For example, neutrinos stopped being connected to each other about 1 second after the Big Bang, but photons stayed balanced with electrons until the universe cooled down enough for neutral atoms to form about 380,000 years later. In a second Big Bang scenario, the thermalization timescales would depend heavily on the maximum temperature reached after the rebirth event and the particle content of the new universe. If the post-bounce temperature exceeded the unification scale of fundamental forces, all interactions, gravitational, strong, weak, and electromagnetic, would be equally strong, and equilibrium would be established almost instantaneously. If the temperature were lower, as might happen in a softer bounce or less energetic brain collision, some interactions might never be strong enough to bring all particle species into equilibrium, leading to a universe with different large-scale properties. The expansion rate itself plays a critical role. This rate is determined by the universe's total energy density through the Friedmann equations. A faster expansion, as might occur in models with extra dimensions or modified gravity, shortens the window during which interactions can occur efficiently. In such a case, thermalization might be incomplete, leaving behind residual inhomogeneities or anisotropies that could shape the later formation of galaxies and cosmic structure. The way matter and radiation work also affects the process. When relativistic particles that move very close to the speed of light, rule the world, interactions happen more often, which speeds up thermalization. On the other hand, stability might take longer to reach if a lot of the post-bounce energy is locked up in huge particles that don't interact with each other very much. Dark matter candidates like WIMPs, weakly interacting massive particles, might separate early, keeping information about the universe's early, out-of-balance state. In very high energy situations, extra processes like plasma turbulence and turbulent cascades can speed up the process of reaching balance. Non-linear effects in the initial plasma quickly move energy between different states, making changes less noticeable. These processes, seen in computer models of quark-gluon plasmas in particle accelerators, may have been used in the very early moments after the Big Bang. In the cosmic microwave background, CMB, you can see the marks of early thermalization. Temperature changes in the CMB are very small, only 1 part in 100,000. This shows that the universe was almost perfectly balanced in terms of temperature on a big scale before photons separated. In a cyclic or rebirth model, the CMB analog's regularity in the new cycle would show how quickly balance was reached after the bounce. High-energy physics at rebirth. If there were to be a second Big Bang, it would start with an amazing amount of energy. At that point, the universe's temperature, density, and curvature would hit levels that are far beyond what we can reproduce in labs today. This Bang 2.0 inches wouldn't just change the structure of the universe. It would also change the basic rules of physics, opening up new areas that maybe not even the first Big Bang fully explored. To guess how the first few seconds of this new world would go, it's important to know the range of particle energies that could be present. In our own cosmic history, the universe began at energies close to the Planck scale, about 10 to the power of 19 giga-electron volts. At these extreme energies, quantum mechanics and gravity are equally important, and the smooth spacetime described by general relativity no longer applies. Instead, quantum fluctuations dominate the very fabric of spacetime, and in this realm, all 4 known forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may merge into a single unified force. If Bang 2.0 reaches similar or even higher energies, it could re-enter this unified regime, briefly erasing all distinctions between the forces. Particle masses as we know them would not exist. Instead, every particle species would be massless and travel at the speed of light, interacting via the same underlying rules. In such conditions, symmetries that are broken in our current low-energy world, like electroweak symmetry, would be fully restored. For many theoretical physicists, the most tantalizing aspect of this energy scale is the possibility of accessing new physics beyond the standard model. If supersymmetry exists, its partner particles would be real and abundant in the ultra-hot plasma, influencing the dynamics of the early universe and potentially altering how it cools. If extra dimensions exist as predicted by some string theory models, they could be large enough at these energies to be fully accessible, changing how gravity behaves and introducing new particle states not seen in our current universe. The range of possible temperatures is huge. Even in a less extreme rebirth, one that doesn't quite reach the Planck scale, but still hits the grand unification scale of about 10 to the power of 16 giga-electron volts, the laws of physics would look nothing like they do today. At this energy, the strong, weak, and electromagnetic forces would merge into a single force, as predicted by grand unified theories. In this phase, high-energy particle collisions could create heavy gauge bosons that let quarks turn into leptons and vice versa, making proton decay a normal event. In our current low-energy universe, such decays are so rare they're almost impossible to observe, but in Bang 2.0, they could happen constantly in the first fractions of a second. The restart temperature could be even lower, between TV and PeV. This might not bring together all the forces, but it could still lead to new discoveries. Dark matter particles, for example, could be made in large amounts and might even take over the energy budget for a while. Some versions of the Standard Model suggest that a lot of heavy sterile neutrinos could appear. These neutrinos could play a part in the uneven distribution of matter and antimatter and in the creation of structure in the new universe. How particles interact at these energies is controlled by the cross-sections of basic processes and the number of possible states. Every type of particle is ultra-relativistic at very high temperatures, which means that they collide very quickly. The plasma that forms is not a gas in the usual sense. Instead, it is a dense, strongly linked medium where collective effects are dominant. It is similar to the quark-gluon plasma that is studied in heavy ion collisions at the Large Hadron Collider, but it is much hotter and denser. At these levels, perturbative quantum field theory, which is usually used to figure out how particles interact, doesn't work anymore. This makes it hard to model this phase theoretically. We need to use non-perturbative effects, quantum gravity corrections, and maybe even whole new models like string theory or loop quantum gravity. These models can predict many things, from the creation of tiny black holes that disappear almost quickly to the appearance of topological flaws such as monopoles, cosmic strings, or domain walls. CMB imprints of previous universes. The cosmic microwave background, CMB, is the oldest light in the universe. It is a nearly uniform sea of microwave radiation that came out of the Big Bang 380,000 years ago, when the universe was cool enough for photons to move easily and neutral atoms to form. Cosmologists use its weak swirls, temperature anisotropies, and polarization patterns to learn a lot about the universe's makeup, age, and shape. But for some experts, the CMB may hold even more, small marks from past stages of the universe. In cycle or bounce cosmologies, the Big Bang is not the very beginning, but rather the change from a phase of contraction to the current phase of growth. If that's true, then some structures or energy patterns from before might have been able to make it through the bounce and spread to the new world. Then, these would leave marks on the CMB, giving us direct proof of a past before the Big Bang. One class of possible signatures is low-variance temperature circles in the CMB sky. Proposed by proponents of conformal cyclic cosmology, CCCC, these circles would arise if massive events in the previous universe, such as supermassive black hole mergers, released vast amounts of gravitational radiation late in that cycle. When mapped onto the geometry of the bounce, these waves could appear as concentric rings, with unusually uniform temperatures in our CMB. While some studies claim tentative detections of such rings, others argue that they are statistical flukes within the limits of cosmic variance. The debate remains unresolved. Another potential clue is anomalous alignments in the CMB's large-scale multipoles, sometimes called the axis of evil. These alignments are difficult to explain in the standard inflationary picture, but in cyclic scenarios, they could be residual directional patterns inherited from the geometry or matter distribution of the previous universe. If the pre-bounce cosmos had a preferred axis or anisotropic features, those patterns might survive expansion and inflation, subtly tilting the large-scale temperature distribution we see today. In bounce models that involve a finite contraction phase, primordial gravitational waves from the previous cycle could also be preserved. These waves would imprint a distinct B-mode polarization pattern in the CMB. The shape and amplitude of this signal could, in principle, be different from the inflationary gravitational wave signature, allowing us to distinguish between the two origins. Current CMB polarization surveys like BICEP-Keck and future missions such as LIGHTBIRD and CMBS-4 are designed to hunt for these subtle signals. There's also the possibility of non-Gaussian temperature fluctuations that deviate from the nearly perfect random distribution predicted by inflationary cosmology. In cyclic models, residual structures from the prior universe could generate statistical hot and cold spots, with correlations not easily explained by quantum fluctuations alone. Detecting such deviations would require extremely precise full-sky maps and careful separation of foreground contamination from galactic dust and synchrotron emission. Some bounce scenarios predict the survival of topological defects from a prior universe, relics like cosmic strings or domain walls, that could produce localized features in the CMB. A cosmic string moving through the photon-baryon plasma before recombination, for example, could leave a line-like discontinuity in temperature across the sky. While no confirmed detection exists, searches for these signatures remain ongoing. Seeing CMB anomalies as proof of past universes is hard, because they are hard to separate from more normal causes. It's possible for foreground leaks, instrumental noise, data processing errors, and statistical coincidences to look like strange features. This is the reason why it's important to use many separate records from projects like Planck, WMAP, and future ones to make a strong case. If genuine pre-Big Bang imprints exist in the CMB, they would revolutionize our understanding of cosmic history. They would provide the first direct empirical evidence that our universe is part of a larger sequence of cycles, confirming that the Big Bang was not the ultimate beginning. More than that, they could offer a way to probe physics at energies far beyond the reach of particle accelerators, since the conditions near the bounce would be encoded in these relic signals. Black hole evaporation as a pre-bounce energy source. In the last few moments of a universe that is about to shrink or crash, black holes could store most of the mass and energy. It is likely that most matter would end up in these gravity pits, as galaxies and stars would die out. The energy that black holes store isn't lost in many circular or bounced cosmologies. It can be reused in the next era of the universe through a process called Hawking radiation. Proposed by Stephen Hawking in 1974, this quantum mechanical effect allows black holes to slowly lose mass by emitting particles and radiation. The mechanism arises because quantum fluctuations near the event horizon can produce particle-antiparticle pairs. One member of the pair falls into the black hole, while the other escapes, carrying away energy. To an outside observer, the black hole appears to be radiating like a blackbody with a temperature inversely proportional to its mass. For supermassive and stellar mass black holes, this temperature is so very low that it is negligible. It is much cooler than the cosmic microwave background we see today. This is why they gain mass from the radiation around them, instead of losing it. On very long timescales, though, as the universe cools down and grows bigger, the background temperature will drop below what even the biggest black holes are thought to be at. After that, evaporation starts. And as the black hole gets smaller, the process speeds up. The last few steps of evaporation are very active. When the mass of a black hole gets close to that of a big asteroid, its Hawking temperature goes up to billions of kelvins. This lets out a huge number of high-energy photons, neutrinos, and maybe even strange particles predicted by theories other than the standard model. In the end, the output could be as strong as the energy that whole galaxies give off. but it would be focused in a very small area of space. In a contracting universe, this process could overlap with the approach to the bounce. As black holes evaporate, their radiation would flood the shrinking cosmos, adding to the overall energy density. If the evaporation rate is significant compared to the contraction rate, this recycled energy could meaningfully alter the pre-bounce conditions. Instead of matter collapsing entirely into singularities, much of it could be redistributed into a relativistic particle bath, increasing the temperature and smoothing the density distribution before the bounce occurs. The energy injection from black hole evaporation might also help reset the entropy balance between cycles. One of the key challenges in cyclic cosmology is avoiding an endless accumulation of disorder from one cycle to the next. Because Hawking radiation is essentially thermal, it disperses the black hole's mass energy evenly across space, potentially diluting high entropy structures and creating a more uniform starting point for the next expansion. If the pre-bounce universe held black holes of many sizes, from tiny primordial ones, born just after the last bounce to colossal galactic cores, their evaporation would unfold over staggered, almost unimaginable timescales. The smallest, with masses under about 10 to the power of 12 kilograms, would have vanished eons before the final contraction. The giants would linger far longer, but as the cosmos drew toward the next bounce, even supermassive black holes could start shedding mass at a rapid pace, unleashing bursts of energy powerful enough to dominate the universe's radiation supply. From a scientific point of view, it would be very hard to find evidence of this kind of pre-bounce evaporation in our own world. Any direct messages would have probably been lost or changed so much during the bounce that they could not be recognized. However, some scientists think that certain statistical aspects of the CMB or an old gravity wave background might hold clues about these kinds of events. As an example, a spectrum of high-frequency gravity waves from the last few seconds of a black hole evaporating might be hidden deep in the cosmic signal and last into the new cycle. Avoiding singularities in quantum cosmology. In traditional general relativity, there are times when singularities can't be avoided. It is shown by the Penrose-Hawking singularity theorems that areas of infinite density and curvature will always exist if matter follows acceptable energy conditions, and Einstein's equations describe spacetime. This happens whether spacetime collapses or rapidly expands. At a singularity, the known rules of physics don't work anymore. Time stops making sense, space doesn't have a clear shape, and it's hard to make predictions. Singularities are a major problem for a world that wants to go through a second Big Bang. There is no way to cross a real infinity. The theory behind it needs to change in order for the universe to go from contracting to expanding without any problems. Quantum cosmology tries to replace these classical infinities with clear, finite values by applying quantum rules to space-time itself. In this view, the smooth fabric of the universe becomes grainy at the Planck scale, about 10 to the power of minus 35 meters. This granularity means that curvature and energy density can't grow forever. Instead, they hit a maximum set by quantum gravity effects. One of the most developed approaches is loop quantum cosmology, LQC, derived from loop quantum gravity. In LQC, space-time geometry is quantized into discrete loops, and the Friedmann equations governing cosmic evolution are modified to include repulsive effects at extreme densities. As a contracting universe approaches what would classically be a singularity, these quantum corrections create a powerful outward pressure. Instead of a collapse to zero volume, the universe undergoes a quantum bounce, smoothly transitioning into an expansion phase. The maximum density reached is finite, on the order of the Planck density, and the geometry remains well behaved. String theory and its higher dimensional extensions are another way to look at it. In some string cosmology models, singularities don't happen because strings and branes, which are the basic building blocks of spacetime, can't be squeezed past a certain length scale. As the universe gets smaller until it hits this limit, The theory adds more spatial dimensions or dualities that change how the geometry is described. This makes the contraction mirror into growth without going through an infinite density state. This feature is used by both the pre-Big Bang and Ekpyrotic situations to connect different stages of the universe without any math problems. A different way to get there is through asymptotically safe gravity. Up to a point in the ultraviolet, the strength of gravity stays the same as the energy scale goes up. When energies get very high, close to the Planck scale, the effective gravitational link lessens. This stops collapses from going too far and avoids singularities. This method keeps a continuum view of space-time while controlling the infinites that are a problem with traditional methods. Some proposals take inspiration from non-commutative geometry, in which the coordinates of space-time fail to commute at very small scales, much like position and momentum in quantum mechanics. This fuzziness of space-time eliminates the sharp localization required to form a true singularity, spreading out energy over a finite region and smoothing the transition between cosmic phases. Keeping away from singularities isn't just a matter of keeping math neat. It has huge effects on how the world works physically. If the bounce takes the place of the singularity, then the conditions of the universe right before the bounce directly affect the conditions after it. There is a chance that information about the last cycle, including its matter makeup, changes, and overall structure, can pass through the bounce and be seen in the new world. In single cosmologies, on the other hand, this data is lost forever. The avoidance mechanisms also influence thermodynamics. In a singular collapse, entropy density would diverge, creating a physically ill-defined state. In quantum bounce scenarios, entropy remains finite, and its distribution across space can be carried into the next cycle. This makes it easier to construct models in which the entropy problem of cyclic cosmology, the tendency for disorder to grow from cycle to cycle, can be addressed in a physically consistent way. From the point of view of sight, singularity avoidance might be possible to test indirectly. Some changes to the early universe equations related to quantum gravity can change the range of primordial fluctuations, which could leave small marks in the cosmic microwave background or the stochastic gravitational wave background. The hard part is separating these signs from the noise and other high-energy processes that might look like them. Topology of space after rebirth. There isn't always a blank slate for a universe's structure when it starts over, whether it's through a bounce, a brain collision, or some other second Big Bang process. The global shape and connections of space are called its topology. It can be limited or infinite, flat or curved, connected in a simple way like a sphere, or in many ways like a cosmic donut. In a rebirth situation, the question is whether this structure stays the same from the last cosmic cycle or is completely reset by the transition's physics. In the standard model of cosmology, general relativity describes the shape of space on a local level, and the total energy density determines how curved space is. This is not the same as topology, though. Even if two worlds have the same shape, their overall structures can be very different. In a flat universe, for instance, the universe could go on forever in all directions, or it could curve around itself like a torus, so going too far in one direction would bring you back to where you started. In a cyclic or bounce cosmology, topological persistence is one option. This means that the form and connections of space stay the same during the bounce. If the universe before the bounce was a three-sphere, then the universe after the bounce would also be closed. If it were a torus or another small manifold, the links might stay the same. They would just get bigger or smaller as the manifold grew. If this happens, any large-scale signs of that structure could last into the new cycle. These could be patterns that repeat in the cosmic microwave background, CMB, or connections between faraway areas. The rebirth could involve a topological reset. In this view, the violent conditions of the bounce, especially if mediated by quantum gravitational effects, could rearrange the connectivity of space entirely. In a brain collision scenario, for instance, the global topology might be determined by how the brains collide and reconnect, potentially leading to a different large-scale structure in each cycle. String theory suggests that the number and shape of compact extra dimensions could also shift between cycles, indirectly altering the topology of the large extended dimensions we experience. The persistence or reset of curvature is tied to these scenarios. If the bounce occurs at extremely high density and temperature, inflation, or a similar rapid expansion mechanism, could occur shortly after rebirth. Inflation has the effect of driving the observable universe toward flatness, erasing most curvature regardless of initial conditions. This would make it challenging to detect whether curvature had persisted from the prior cycle. Without such a smoothing process, residual curvature from the pre-bounce state could be measurable today. Some models, such as conformal cyclic cosmology, allow curvature to persist but become irrelevant at the transition because the geometry is rescaled to such an extent that it appears flat. Others, like certain loop quantum cosmology scenarios, predict that curvature and topology are directly tied to the quantum state of space-time, meaning the bounce could fully determine the new cycle's geometry. Finding cosmic topology is extremely hard to do. In the CMB sky, scientists look for patterns that look like matched circles. These patterns would show up if light had gone around the universe and come back from different directions. They also look at studies of many galaxies to find patterns or strange connections. If these patterns were found, they could be compared to what bounce models say will happen to see if the topology is a cosmic holdover or a new mark from the restart. For circular cosmology, a lot is at stake. If topology stays the same, it could provide an observational link between cycles, letting us piece together parts of a world that existed before ours. It means that each cycle is more like a restart than a continuation, with the large-scale structure appearing again from the physics of the bounce. Extra dimensions in brane collision models. When you look at string theory and similar ideas, you can see that reality is made up of more than just space and time. The universe might instead be a brane, which is a three-dimensional area inside a higher dimensional space known as the bulk. Branes are not just scenes from science fiction. They are basic parts of theories like M-theory, which says that there could be up to 11 dimensions, with 7 of them curled up into shapes much smaller than an atom. In this picture, the world we can see is just one brane out of many that could exist. Each one floats in the bulk of higher dimensions. The Ekpyrotic and Cyclic brane collision models use this framework to explain the Big Bang, and by extension, how a second Big Bang could occur. In these models, the bang is not the creation of space and time from nothing, but the result of two branes colliding in the bulk. The kinetic energy of that collision is converted into the hot, dense plasma that becomes our universe. When the branes rebound and move apart, cosmic expansion begins. Over immense stretches of time, the branes are pulled together again by higher dimensional forces, setting the stage for another collision and another cycle. The extra dimensions in these scenarios are not idle background scenery. They actively shape the physics of the next universe. The geometry of the compact dimensions, their size, shape, and curvature, determines fundamental constants like the strength of gravity, the masses of particles, and the behavior of forces. A slight shift in the compactification of extra dimensions after a collision could produce a universe with slightly different physical laws. During a brane collision, the energy distribution across the brane may not be uniform. Local variations in impact energy could see density fluctuations that later grow into galaxies and clusters in the new universe. These variations might be influenced by the geometry of the bulk or by the position of other branes nearby. If the bulk contains warped regions, areas where distances in the extra dimensions are distorted, these could funnel or concentrate energy into specific locations during the collision, potentially leaving imprints on the large-scale structure of the cosmos. This idea that gravity is not limited to our brane is one of the most important parts of brane world physics. Light and matter are stuck on the surface of our three-dimensional world, but gravitons, which are made-up particles of the gravity field, can move into or through the other dimensions. This loss changes how gravity works on both very large and very small scales. It could also change how a universe that is shrinking before it collides. In some models, the bulk's gravitational pull can help start or direct the time of the brane approach. This means that the next Big Bang can be predicted by the geometry of higher dimensions. The extra dimensions may also act as energy reservoirs. Vibrations, twists, or changes in their shape, known as moduli, can store energy during the expansion and release it during contraction or collision. This could contribute to reheating the universe after the bang or influence the particle content of the newborn cosmos. In some scenarios, particles from the higher dimensional bulk could even be injected into the brane during the collision, introducing new species of matter into the next cycle. Detecting evidence of extra dimensions remains a challenge. On the cosmological side, certain patterns in the cosmic microwave background or the distribution of large-scale structures could hint at brane world origins. On the experimental side, high-energy particle collisions might produce missing energy signatures if gravitons escape into extra dimensions. Phase transitions after a second bang. The universe would be a scorching high-energy plasma right after a second Big Bang, which could have been caused by a brane collision, a quantum bounce, or something else completely different. Matter and forces would not yet be different from each other at these temperatures. Instead, the world would be controlled by unified patterns, which make it impossible to tell the difference between different natural forces. As the universe cools down and expands, these patterns go through a number of phase changes. This is similar to how water freezes into ice, but on a much larger scale in terms of energy and space than is possible in a lab. The first of these transitions would happen at the grand unification scale, around 10 to the power of 16 giga-electron volts. At this energy, scientists think the strong nuclear force, the weak nuclear force, and electromagnetism all merge into one single force, described by a grand unified theory or GUT. As the universe cools below this point, that unified symmetry breaks apart, separating the strong force from the electro-weak interaction. This breaking of symmetry would release an enormous amount of energy and could create relics like magnetic monopoles, particles with only one magnetic pole, unless inflation or other processes dilute them. After this, the world would go through the electroweak phase shift, which is where the weak force and electromagnetic fields become separate. This happens when the Higgs field, which is the quantum field that gives particles their mass, falls into a state other than zero. Right now, particles like the W and Z bosons are getting heavier, but the photon is still not having any mass. The exact structure of the electroweak shift is very important for understanding how the universe evolved. It could create a background of gravity waves that could be seen today if it is a first-order phase transition that goes through the formation of bubbles in the new phase. Baryogenesis, the process that explains why there is more matter than antimatter in the world, needs conditions that are not in balance. This could be created. As cooling continues, quantum chromodynamics, QCD, takes over. At about 170 megaelectron volts, quarks and gluons, the building blocks of protons and neutrons, become confined into hadrons. This QCD confinement transition marks the emergence of stable nuclear matter. Before this point, the universe is a quark-gluon plasma, a dense soup where individual protons and neutrons cannot exist. The transition locks most quarks into protons and neutrons, setting the stage for later nuclear fusion in stars. These early transitions are not purely structural changes. They are also engines for shaping the observable cosmos. Symmetry breaking can create topological defects such as cosmic strings, domain walls, or textures, depending on the nature of the underlying fields. While many such defects would be diluted or destroyed by inflation, some models predict that traces could survive, influencing structure formation or leaving faint imprints in the cosmic microwave background. If inflation happens after the second bang, it is linked to a phase shift. This is when the inflaton field goes from being a high-energy vacuum state to a lower-energy one, A huge amount of radiation would be released during this process, which would also set the stage for the hot Big Bang phase. There could be more than one inflation-like burst in some situations, each one caused by a symmetry-breaking event in a different area of physics. As soon as temperatures drop low enough, nuclear processes can start. Now is the time of Big Bang nucleosynthesis, BBN, which is when protons and neutrons join together to make hydrogen, helium, and small amounts of lithium. The exact time and effectiveness of BBN depend on the results of earlier phase changes, which decide the masses of particles, the strength of the interactions between them, and the number of baryons present. Phase transitions in a post-rebirth universe could differ from those in our own cosmic past. If extra dimensions, modified gravity, or exotic fields are involved in the rebirth mechanism, the sequence, timing, and even the types of transitions could change. The constants that define particle interactions might shift slightly, producing a universe with similar large-scale behavior, but subtle differences in chemistry, stellar evolution, or galaxy formation. Re-triggering cosmic inflation. Cosmic inflation, a short time of exponential growth in the first fraction of a second of the universe, is what makes the cosmos smooth on a large scale, the cosmic microwave background uniform, and the start of primordial density fluctuations. In normal cosmology, inflation only happens once. It is caused by the inflaton, a scalar field, falling from a high-energy state to a low-energy state. But if the universe has already fallen and then reformed into a second Big Bang, could this process begin again? If so, how would it happen? A scalar field with a potential energy curve that is flat enough is essential for inflation to happen. In the inflationary model, the field rolls this potential down slowly, keeping its energy density almost the same for a short but important time. This steady amount of energy works like a force that pushes against gravity, making space expand faster than the speed of light, in terms of measure expansion, not motion through space. When the field hits the steeper part of the potential, expansion stops. The stored energy is then reheated and turned into a hot bath of particles. After a cosmic collapse or bounce, re-triggering inflation would require the inflaton, or another scalar field with similar properties, to be placed high on its potential again. In some models, this happens naturally. If the inflaton is part of the fundamental structure of spacetime, the extreme compression of the universe during contraction could push the field back up the potential. When the bounce occurs, the field would begin rolling down again, initiating a fresh round of inflation. Other scenarios rely on the dynamics of extra dimensions or brane collisions. In cyclic brane world models, each collision resets the scalar fields associated with interbrane separation, placing them into a high-energy configuration that naturally fuels inflation in the post-collision universe. The specific shape of the potential, determined by higher dimensional physics, governs both the duration of inflation and the amplitude of the density fluctuations it produces. Re-triggering inflation also depends on avoiding thermal domination before the process begins. If the bounce releases too much high-energy radiation immediately, it could swamp the potential energy of the inflaton and prevent inflation from starting. This is known as the initial conditions problem in post-bounce inflationary models. Successful scenarios often require the bounce to be relatively cold, with most of the energy initially stored in fields rather than in particles. This allows the inflaton's vacuum energy to dominate the expansion until the rapid growth phase has done its work. The duration of inflation is critical. To solve the flatness and horizon problems in a second bang scenario, inflation must still last for at least 60 e-folds of expansion. However, too much inflation would erase any observable imprints from the previous cosmic cycle, such as relic gravitational waves or subtle anomalies in the CMB. This creates a balance point for theorists. Inflation must be long enough to explain the smoothness of the current universe, but not so long that it wipes away all traces of the past. Another important thing to think about is the quantum changes that happen during the inflationary phase. In normal inflation, these changes are blown out to the size of the universe, and start the process of galaxies forming. If pre-bounce physics changed the original state of the inflaton in a second bang, the fluctuation spectrum might have unique traits, such as non-Gaussian patterns or a cutoff at large scales. With accurate measures of the CMB or large-scale structure studies, these differences might be able to be put to the test. Thermodynamics also limits how inflation can be started up again after it has stopped. The field needs to be able to repeat the same process without adding to the entropy from the last turn. Some cycle models try to explain this by saying that the inflationary phase itself lowers entropy, which is like resetting the universe for the next round of evolution. Inflation is not only a way to make space smoother, but it is also a way for the mess of past epochs to be erased from the universe. Matter recycling between cycles. If the universe goes through cycles of growing, shrinking, and rebirthing in ways similar to the Big Bang, then the question of what happens to matter from one cycle to the next becomes very important. Does everything just disappear and be replaced by brand new particles? Or can leftovers from one cosmic era cause the matter in the next to grow? One very strong option is that black holes recycle matter by carrying it through the changes between rounds and releasing it in the new universe. Black holes are the ultimate places for matter to go in our world. Anything that crosses their event horizon gets caught and squished into a very dense singularity, or in quantum gravity models, a very small but very extreme core. This includes gas between stars and whole stars. In a cyclic universe, these black holes might be able to stay alive well into the contraction phase, long after gravity has pulled regular matter together. Many models of quantum cosmology say that singularities should not exist. If they do, the cores of black holes could be used to store matter in a way that is steady and very dense across the bounce. One way matter might re-enter the new cycle is through Hawking radiation. Over immense timescales, black holes evaporate by emitting thermal radiation, a process predicted by quantum field theory in curved spacetime. In a rebirth scenario, this evaporation could occur during the final stages of contraction, releasing stored mass energy into the collapsing universe. When the bounce or new bang occurs, this liberated energy would join the high-energy plasma of the new expansion phase. In certain loop quantum gravity or string theory-inspired models, black holes might not fully evaporate. Instead, they could leave behind stable remnants, compact objects with a finite Planck-scale mass. These remnants could survive the bounce intact, carrying information and matter content from the old universe into the new one. If the new universe's physics allows these remnants to decay or interact, they could become the seeds of baryonic matter, contributing to the formation of protons, neutrons, and ultimately atoms in the reborn cosmos. Some cyclic cosmologies go further, suggesting that the interiors of black holes could themselves be new universes. In this view, every black hole in our universe is a gateway to a separate expanding spacetime. If the bounce connecting cycles operates through a network of such baby universes, then matter might not only be recycled, it could be redistributed into multiple cosmic offspring. The next cycle of our universe could be seeded by the accumulated mass of countless black holes from the previous cycle, compressed and then released in a single global event. There's also the chance of reusing some of it. As the contraction continues, extreme gravity forces and tides could tear apart big structures, feeding black holes more quickly. The bounce's mass energy distribution might be very different from how it started during the previous growth, but it can still be linked to the matter's past. In this way, black holes wouldn't keep every detail of the old world, but they would make sure that mass energy doesn't get lost and is instead used again. From the point of view of thermodynamics, recycling matter between cycles might help solve the entropy problem in circular cosmologies. Normal for entropy, a measure of chaos, to rise from one cycle to the next, which means that each new world is more chaotic and less organized. If black holes collect matter and then spread it out again in a concentrated form, they might be able to control entropy and smooth out some of the chaos before the next cycle starts. However, this is still a controversial idea because Hawking radiation has a high entropy and could make the problem worse instead of better. It's difficult to confirm whether matter in our universe is recycled from an earlier one, but subtle clues might be embedded in the cosmic microwave background or in the statistical distribution of matter on the largest scales. For example, if stable black hole remnants from a prior cycle exist in our current universe, they could contribute to the dark matter population, influencing galaxy rotation curves and gravitational lensing without emitting light. Anisotropy evolution across bounces. Anisotropy means that the big picture features of the world are not all the same in every direction. The cosmic microwave background, CMB, shows us that the universe is very isotropic, which means it is the same in all directions to within 1 part in 100,000. However, there are very small anisotropies that exist, and they are what galaxies and other cosmic structures are made of. But in a circular or bouncing universe where a contraction comes before a new Big Bang, the question is whether these changes in direction stay the same during the bounce, or are they lost? The problem is rooted in BKL instability, named after Belinsky, Kalatnikov, and Lifshitz, which predicts that, as a universe contracts toward a singularity, anisotropies can grow dramatically. Even if the cosmos starts out nearly uniform, gravitational tidal forces along different spatial axes can amplify tiny directional differences, potentially creating a chaotic anisotropic state before the bounce. In the absence of new physics, this would make it nearly impossible for a contracting universe to produce the smooth isotropic conditions observed after a Big Bang. Some cyclic models tackle this problem head-on. In Ekpyrotic cosmology, the contraction phase is driven by a scalar field with an ultra-stiff equation of state, where pressure greatly exceeds energy density. This high pressure counteracts the growth of anisotropies, smoothing the universe before the bounce occurs. The result is that any directional differences are exponentially suppressed, leaving a clean, nearly isotropic starting point for the next expansion. Loop quantum cosmology offers a different solution. Here, quantum gravity effects modify the Einstein field equations at extremely high densities, introducing terms that effectively bound the growth of anisotropies. Instead of diverging toward a singularity, directional differences reach a maximum amplitude before being damped or transformed during the bounce. In some formulations, anisotropies can be transferred into specific quantum degrees of freedom, effectively hiding them from the classical universe that emerges afterward. Not all models erase anisotropy completely. In certain non-singular bounce scenarios, a small fraction of directional information can persist across the transition. If so, the newborn universe could carry a faint memory of the prior cycle's anisotropy, possibly encoded in subtle polarization patterns in the CMB or in the alignment of large-scale cosmic structures. These relic signatures would be extremely hard to detect, but they could offer a rare observational window into pre-Big Bang physics. Anisotropy's fate is also affected by how long and how much energy they have after the bounce. Any anisotropy that was there before will be diluted to levels that can't be seen during a long, high-energy rising phase. This will erase the memory of earlier cycles. But if the inflationary phase is short or not there at all, there is more room for leftover anisotropy to stay alive. This makes a scientific trade-off. The world looks smoother and cleaner now, but it's harder to find proof of cycles that happened in the past. There is also the matter of curving in a certain way. Anisotropic cosmologies, like Bianchi models, allow curves to change along different lines in space, which changes how contraction and expansion happen. If these curve anisotropies make it through the bounce, they might leave unique patterns in the way matter is distributed, or in the way galaxies move at very large scales. There isn't a lot of strong proof for these kinds of trends right now, so the amount of anisotropy that can last from one cycle to the next is limited. Whether anisotropy survives a bounce depends on the physics governing the transition. If the bounce is mediated by classical general relativity alone, anisotropy growth is a severe problem. But if new physics, such as scalar fields with special potentials, higher dimensional effects, or quantum gravitational corrections, is in play, anisotropy can be damped, erased, or even transformed into other forms of energy before the expansion begins. Scalar field oscillations and reheating. In many cosmological models, including the normal Big Bang and cyclic ones, the end of a high-energy phase like inflation or a cosmic bounce doesn't mean that the universe goes from being mostly empty to being full of particles right away. Instead, it goes through a key bridge period called reheating. During this time, scalar fields move around the lowest point of their potential and put energy into a dense, hot plasma of particles. This process is very important for making the matter and radiation that will eventually connect galaxies, stars, and planets into a web. The scalar field that causes fast growth in an inflationary context is known as the inflaton. In a world that cycles or bounces, this field could be the same inflaton, a related scalar, or a field that comes from processes outside of space and time. Most of the time, the scalar field is close to the bottom of its potential well after the bounce or the end of the inflation-like growth. It doesn't stop right away. Instead, it overshoots and starts to bounce. These vibrations aren't just math mistakes. They're a real source of energy that can be used to make the particles that make up the new universe. The mechanism of energy transfer from scalar oscillations to matter fields depends on how the scalar couples to other particles. If the scalar is directly coupled to bosons or fermions, it can decay perturbatively, gradually releasing its energy into a thermal bath. The decay rate is determined by the coupling constants and the scalar's mass. For strong couplings, the transfer is rapid, leading to quick thermalization. For weaker couplings, reheating is slower, delaying the point at which the universe becomes radiation-dominated. Reheating is not always just a perturbative process. It is possible for the changing scalar field to interact resonantly with certain particle modes, which can cause those modes to become exponentially stronger in a process called parametric resonance. This can cause big changes in certain types of particles that aren't warm. This can make the universe's energy distribution very uneven, until later scattering processes even things out. Preheating is very good at making bosonic fields, and it can also cause complex nonlinear dynamics, such as the creation of oscillons, which are localized field configurations. It is also possible for reheating to cause gravity waves. Scalar fields vary and decay, which causes uneven stresses in the energy-momentum tensor. These stresses can make a random gravity wave background. If there is a second Big Bang, these gravity waves might carry traces of the bounce's energy scale and dynamics. This could be used as an observational test if their frequencies and amplitudes are within the ranges that current or future instruments can pick up. Thermalization, the point at which the universe's energy distribution becomes uniform and describable by a temperature, is a critical milestone. Before this stage, particle populations may be far from equilibrium, with different species having different energies or distributions. Through scattering and decays, the system approaches a thermal state, and the temperature of the universe becomes a meaningful concept. The reheating temperature marks the beginning of the radiation-dominated era and sets the stage for processes like Big Bang nucleosynthesis. In cyclic models, the specifics of scalar waves and warming could be very different from the Big Bang in our universe. The main way the universe becomes livable for matter is through warming. This happens when the bounce is cold, meaning that most of the energy is stored in fields instead of hot radiation at the point of transition. In warm bounce situations, where some radiation is already present, scalar oscillations may still play a role in figuring out the total energy budget, but they may not be as important. There is also the chance that scalar fields connect to secret sectors, which are groups of particles that don't interact strongly with the standard model. In this case, some of the warmed energy might end up in dark matter or other strange leftovers. This might change the amount of matter to radiation in the new universe and leave marks in the formation of cosmic structures or the cosmic microwave background. Large-scale structure constraints. Any good model of a second Big Bang needs to do more than just make the universe hot and dense. It also needs to make the complex web of structures in the universe that we see today. It is made up of galaxy groups, strands, and empty spaces that stretch over hundreds of millions of light years. This web is called the large-scale structure, LSS, of the universe. It's not random that this structure's density changes, grouping patterns, and association scales are the way they are. A lot of information from galaxy studies, readings of the cosmic microwave background, CMB, and gravitational lensing keeps them in a tight range. In order for a rebirth model to fit with what we see, it has to match these limitations very closely. The first challenge comes from primordial density perturbations. In the standard cosmological model, these tiny fluctuations were generated during inflation as quantum fluctuations of the inflaton field later stretched to cosmic scales. They follow an almost scale-invariant power spectrum, meaning their amplitude changes only slightly across different length scales. In a second bang scenario, these perturbations could be generated either by a new inflationary phase or by alternative mechanisms, such as the amplification of vacuum fluctuations during a bounce. In either case, the resulting spectrum must match the near-scale invariance observed by the Planck satellite, with a spectral index n_s close to 0.965. A second Big Bang also has to get the amplitude of fluctuations right. The current universe's galaxy distribution implies a fluctuation amplitude on the order of sigma_8 per proc 0.8, where sigma_8 measures the root mean square variation of the density field on scales of 8 megaparsecs. If the second bang produces fluctuations that are too strong, matter will collapse into massive structures too quickly, leaving fewer large voids and distorting the galaxy correlation function. If they are too weak, galaxies form too slowly, and the cosmic web becomes underdeveloped compared to observations. The baryon acoustic oscillations, BAO, are another important restriction. They are the fossils of sound waves that moved through the primordial plasma before they mixed again. It can be seen in both the CMB and the way galaxies are spread out that BAO leave a chosen clustering size of about 150 megaparsecs. For these waves to happen, a second bang scenario must not only create a similar plasma environment, but it must also make sure that the sound horizon at recombination fits the BAO scale that we see today. Any change would show up as a mismatch in the grouping pattern in studies of galaxy redshift. The matter power spectrum test is even more in-depth. Surveys like SDSS, DESI, and Euclid measure this function, which shows how changes in matter density are spread out as a function of size. Its overall shape must be reproduced by the rebirth model. This includes a broad peak at the BAO scale, a smooth drop at smaller scales due to silk damping, and the right tilt set by the starting conditions. If you change the path of expansion, the rate at which structures grow, or the qualities of dark matter between cycles, you might get a spectrum that doesn't match what we see. LSS constraints also extend to the growth rate of structure over cosmic time. Redshift space distortion measurements, which track how galaxies fall toward dense regions, are sensitive to the gravitational physics driving cosmic evolution. If the second bang produces a universe with modified gravity, different dark energy behavior, or unusual dark matter properties, the growth rate could differ from the predictions of the standard LCDM model. This difference would be measurable in large surveys, potentially ruling out models that otherwise reproduce the CMB. The alignment of LSS with CMB anisotropies is another test. In our universe, the largest structures, such as the Sloan Great Wall and vast cosmic voids, correlate statistically with temperature fluctuations in the CMB via the integrated Sachs-Wolf effect. A second bang must preserve this alignment if it wishes to match both early and late-time observations. Failure to do so would hint that the large-scale modes present after the bounce differ fundamentally from those produced in our universe's inflationary epoch. There's also the issue of non-Gaussianity. In the standard model, the primordial fluctuations are almost perfectly Gaussian. Their statistical spread follows a simple bell curve shape. Any major deviation from this would leave clear marks in the way galaxies are distributed, especially across the largest scales. Second bang scenarios that involve certain bounce mechanisms or unusual field behavior could produce more non-Gaussianity than what current observations allow. The Planck satellite's strict limits on the nonlinearity parameter, known as FNL, put strong constraints on which of these models can still be considered possible. Background from past cycles. Neutrinos were able to see right through the universe long before light could. These almost massless particles that only slightly interact with each other broke away from the hot plasma when the universe was only 10 billion kelvins old, or about 1 second old. Following that, they have moved freely through space, cooling with the expansion of the universe until they are now only 1.95 kelvins hot, which is cooler than the cosmic microwave background, CMB. This strange sea of particles is called the cosmic neutrino background, CNB, and it is thought to be one of the oldest remnants of the Big Bang. In a second Big Bang scenario, the CNB could serve as an even deeper time capsule, potentially carrying imprints from earlier cosmic cycles. Unlike photons, which are easily scattered and absorbed, neutrinos interact so weakly with matter that they can preserve information from extremely early times. If the universe has gone through previous expansions and contractions, relic neutrinos might bear subtle signatures of physics predating the most recent bang. The challenge is that these neutrinos are extremely hard to detect. Today, they have an average energy of only about 10 to the power of -4 electron volts, far too low for most particle experiments to pick up. We only know they exist indirectly by seeing how they affect things like the CMB power spectrum or the way galaxies form on large scales. But direct detection remains the ultimate goal. Several proposed experiments like Ptolemy, short for Princeton Tritium Observatory for Light, Early Universe, Massive Neutrino Yield, aim to do this by capturing relic neutrinos through neutrino capture on beta-decaying nuclei. The CNB's features might be slightly different from what a single bang universe says they are in cycle cosmologies. For example, the number density of relic neutrinos could change if the warming temperature in the previous cycle was higher or lower than the one we are in. This would affect the neutrino's energy balance. Also, if there were new particle types in a previous cycle and they broke down into neutrinos before the bounce, they could add a non-thermal spectrum, which is different from the smooth Fermi-Dirac distribution that is expected in normal cosmology. Neutrinos' mass order and mixing patterns are another thing that could be a sign. Neutrinos in the standard model have very small masses that are not zero and change tastes all the time. If the bouncing or second bang changed the universe's vacuum structure, it might have changed these angles of mass breaking or mixing in ways that we might still be able to see today. A past that is more complicated than a single 13.8 billion year timescale could be shown by even small changes from what we know now. The CNB could also preserve directional anisotropies from past cycles. In our universe, the CNB should be almost perfectly isotropic, with only minute variations caused by our motion relative to its rest frame, the so-called neutrino dipole. But if the bounce allowed certain large-scale anisotropies to survive, they could show up as preferred directions in the relic neutrino background, offering an unprecedented probe of pre-Big Bang physics. There's also the possibility of topological relics encoded in neutrino properties. Certain grand unified theories predict the formation of topological defects, such as cosmic strings or domain walls, in the early universe. If such structures formed in a previous cycle and decayed into neutrinos before the bounce, the resulting background could carry imprints of their decay patterns, imprints that might survive into the current cycle. From an observational standpoint, teasing out these signatures would require not only detecting the CNB directly, but also measuring its energy spectrum and angular distribution with exquisite precision. That's a tall order, given that relic neutrinos have wavelengths on the order of millimeters and are moving at sub-relativistic speeds today. However, the payoff would be extraordinary, a direct glimpse into conditions billions or even trillions of years before the birth of our observable universe. Methods that aren't direct could help close the gap until direct identification is possible. Cosmological studies can limit the number of neutrino species by comparing the CMB with data on how galaxies are clustered. A number that is different from the expected value of about 3.046 could mean that there are extra neutrino-like particles from an earlier cycle, or that the CMB is distorted because of bounce dynamics. Also, gravitational lensing maps might show small changes in the way structures are growing that are in line with a changed Relic neutrino background. Magnetic field survival through bounces. Magnetic fields are found everywhere in the universe, inside galaxies, between galaxy clusters, and even across the cosmic web. Even the vast voids between galaxies contain faint magnetic fields, about 10 to the power of -15 Gauss. These fields influence many important processes, from how stars form to how cosmic rays are accelerated. But their origin is still a mystery. One leading idea is that they started as weak primordial magnetic fields in the early universe, which were later strengthened by galactic dynamos. A big question comes up in a second Big Bang or cyclic cosmology scenario. Could this kind of primordial magnetism survive the fall of a universe and show up again in the next cycle? Or would the rough physics of a bounce wipe out these fields completely, making them start over with each cycle? In a world that is growing, magnetohydrodynamics, MHD, describes how magnetic fields change over time. It combines Maxwell's equations with the movement of charged fluids. Cosmic magnetic fields are frozen into the plasma when there aren't any strong resistance effects. This means that their power goes down as the square of the scale factor goes up. When the universe expands, this makes the fields weaker. But when it contracts, the opposite happens. The fields get stronger as the universe gets smaller. In a purely classical bounce, where contraction simply reverses into expansion, primordial magnetic fields could, in principle, survive and even be amplified. However, reality is more complicated. The approach to the bounce involves extreme curvature, high-energy particle interactions, and possibly quantum gravitational effects. Each of these can alter the plasma conditions that keep fields frozen in, potentially dissipating them. In particular, if the conductivity of the cosmic medium drops, magnetic reconnection could destroy large-scale field coherence. Some cycle models actively help magnetic fields stay alive. In loop quantum cosmology, the bounce happens at a fixed temperature and density, so there is no infinite compression of a singularity. This keeps the magnetic field constant and limited during the bounce, just changing the way it dilutes when growth starts up again. Furthermore, in ekpyrotic and brane collision models, three-dimensional geometry can act as a solid background, letting gauge fields like electromagnetic waves pass through the shift largely unaltered. Inflationary stages that happen after the bounce, which are common in many models to explain large-scale isotropy, tend to weaken any magnetic field that was there before the bounce to almost nothing. This means that even if fields survive the bounce, they would lose their power during a strong inflationary period after the bounce. This would mean that they would have to be restored using the Biermann battery, or quantum changes of the electromagnetic field in curved space-time. If primordial magnetism does survive, its correlation length and spectral shape could provide clues to the physics of the bounce. For example, turbulence during contraction might imprint a characteristic scale in the magnetic power spectrum, preserved into the next cycle. Detecting such a signature in today's intergalactic fields could offer indirect evidence for a pre-Big Bang origin. From an observational standpoint, the key lies in ultra-weak magnetic fields in cosmic voids. These fields, detected indirectly through gamma-ray observations of blazars, are too weak and too large-scale to be easily explained by galactic outflows alone. If their properties match predictions from cyclic models with magnetic survival, they could represent one of the few surviving physical links to a prior universe. Along with this, there is a slight relationship with cosmic conductivity. If the conductivity stays very high during the whole sequence of contraction, bounce, and expansion, field lines will stay tightly bound to the plasma, which will keep the large-scale coherence. But if conductivity drops because of the creation of strange particles or phase changes, resistive loss could separate field lines, wiping out memories of earlier cycles. Because of this, bounce models naturally fall into two groups: those with strong field continuity and those where magnetogenesis has to start over every cycle. What happens to initial magnetism during a bounce is not only an interesting question in astrophysics, but it can also be used to test how smooth or rough the bounce is. A smooth, non-singular change could let magnetic fields pass through mostly unharmed, but a rough high-energy restart could spread them all over the place. Shifts in fundamental constants after rebirth. The universe is based on a set of numbers that look like they were carved into the ground. The speed of light c, Newton's gravity constant, g, the fine structure constant alpha, Planck's constant h, and other fundamental constants govern how forces combine, how particles behave, and how the cosmic story develops. If we change them even a little, the science we think we know could be completely changed. The way normal astronomy sees it, these things are always the same, not changing in space or time. There is no promise, though, that the constants of one cosmic cycle will be the same as those of the next in the case of a second Big Bang or a circular universe. In theory, a bounce could change the underlying vacuum state or the shape of extra dimensions, which would mean that the physical law's dial settings would be slightly changed. Alternative theories, like string theory and scalar tensor gravity, give us a reason to think about these kinds of changes. Constants like alpha or g are not fixed sources in these systems. Instead, they are dynamical quantities that are set by the values of scalar fields. If those fields move during the process of collapse, bounce, and growth, the constants they control might have slightly different values in the next cycle. Take the fine structure constant alpha, which measures the strength of the electromagnetic force. It is dimensionless, making it a favorite target for precision tests of variation. A fractional change in alpha, as small as 1 part in a million, could shift atomic energy levels enough to alter the spectra of distant quasars. Astronomers have already looked for such variations across cosmic time, with mixed results. Some datasets hinting at a spatial or temporal drift, others finding no deviation. In a rebirth scenario, a bounce could produce a uniform reset of alpha across space, or even a patchy distribution if the transition is not perfectly homogeneous. Newton's gravitational constant g presents a different challenge. A change in g affects the strength of gravity itself, altering stellar lifetimes, the dynamics of galaxy formation, and the balance between radiation and matter in the early universe. In scalar tensor theories, g is inversely related to a scalar field that can evolve over time. If the collapse phase of a prior cycle excites this field, the post-bounce universe could inherit a slightly altered gravitational strength. Even a percent-level change could leave fingerprints in the cosmic microwave background and the large-scale distribution of galaxies. Time and space are more deeply connected to the speed of light, c. People have suggested varying c models as a way to solve cosmic questions like the horizon problem without inflation. However, these models are controversial because c shows up in a lot of basic equations. Some brain-world or extra-dimensional models say that the effective c that particles in our 3D universe feel might depend on the shape of other dimensions. If these dimensions are rearranged by a bounce, the speed of light might change slightly in the new cycle. It's hard, but not impossible, to test for changes in constants after a made-up second bang. Astrophysical probes can help. Quasar absorption spectra can test changes INN, pulsar timing arrays, and gravitational wave observations can limit changes in g, and precise CMB measurements can show changes in the history of ionization that are connected to changed constants. Some of the tightest limits on present-day drift rates have been set in the lab through atomic clock comparisons. However, these studies don't tell us much about how clocks restart completely at a bounce. From a theoretical perspective, changes in constants after a bounce would likely be tied to symmetry breaking in the early universe. For example, if the Higgs field settles into a slightly different vacuum expectation value after the bounce, particle masses could shift. The strong nuclear force might become marginally stronger or weaker if the quantum chromodynamics, QCD, coupling changes, potentially altering nuclear binding energies and even the periodic table of stable elements in that cycle. The effects on being able to live there are huge. Small changes to constants in some parts of parameter space could weaken chemistry, make stars less stable, or even stop complex cores from forming. In others, they might not change the structure on a big scale, but they could have a huge effect on the temperatures or chemistry of life on other planets. This brings up the interesting idea that even if the world cycles forever, not every cycle would be the same for people like us. Transfer of cosmological perturbations between cycles. Small changes from perfect regularity in the universe's density and shape are called cosmological perturbations. They are the building blocks of all structure. They started out as quantum fluctuations in our universe. During inflation, they grew to cosmic proportions, and then gravity pulled them back together to form galaxies, clusters, and the cosmic web. In a cyclic or second Big Bang model, however, there is a crucial question. Could these changes survive the crash and bounce, leaving their mark on the next cosmic cycle? It is the theory of linear perturbations in general relativity that describes perturbations. The comoving curved perturbation is often used to describe perturbations. This number is very important because it stays the same on super-horizon sizes in a world with only one perfect fluid. This conservation feature means that, in an ideal world, large-scale effects might stay the same even if the cosmic environment changes dramatically, which could include a bounce. The fate of these perturbations in a collapsing universe depends heavily on the physics near the bounce. In a purely classical collapse governed by Einstein's equations, perturbations can grow dramatically, especially anisotropies, directional distortions in the expansion, and certain curvature modes. This is known as the BKL instability, and in the absence of new physics, it could overwhelm the smoothness needed for a clean rebound. If the bounce is mediated by quantum gravity effects, exotic matter with negative pressure, or higher dimensional brane collisions, these instabilities might be suppressed, allowing the large-scale perturbations to pass through relatively intact. Some cyclic models, such as the Ekpyrotic scenario, have been designed with exactly this in mind. In ekpyrosis, the collapsing phase is dominated by a scalar field with a steep negative potential. This causes the universe to contract slowly in a highly anisotropy-suppressing way, smoothing and flattening space while converting quantum fluctuations in the scalar field into nearly scale-invariant curvature perturbations. These perturbations can, under the right conditions, be matched across the bounce into the expanding phase, providing the seeds for structure in the new cycle without the need for a traditional inflationary burst. The scientific problem is that the variables at the bounce have to match up just right. First-order differential equations in time describe perturbations. When the scale factor is at its lowest, some terms can become singular if new physics doesn't make the bounce regular. To let perturbations go through, you need to show how the measure and its derivatives are linked before and after the bounce. There are various types of bounce processes, such as quantum loop gravity, ghost condensates, and higher dimensional brane dynamics. Each of these has its own matching rules, which can have a big impact on whether modes are kept, deleted, or even amplified. Entropy, isocurvature perturbations are another problem. These are changes in the relative number levels of different parts, like photons, baryons, and dark matter. These entropy modes can change into curve perturbations and back again in many multi-field models. In other words, even if some curve perturbations are lost during the bounce, they might be able to come back from surviving entropy modes, which would change the statistical features of the perturbations in the next cycle. If perturbations do make it to the new universe, their power range might still show clear signs of the old cycle. As an example, some cyclic models say that power will be lowered on the biggest sizes, the spectrum will oscillate a little, or the spectral index will run in a complicated way. It's possible that these traits can be seen in the cosmic microwave background of this cycle. This could help us find signs of a universe that existed earlier. Non-Gaussianities, deviations from a purely Gaussian statistical distribution of perturbations, also play a role. While inflation in our cycle produces perturbations that are nearly Gaussian, bounce models can naturally generate larger non-Gaussian signatures, depending on the dynamics of the fields involved. If those signatures survive the bounce, they could be a powerful discriminator between a universe born from nothing and one reborn from a prior cycle. Gravitational waves are another way that data can be sent. Primordial tensor modes are the ripples in space-time that are caused by changes in density. They may act differently when space-time is expanding or contracting. Tensor modes are pushed down compared to scalar modes in some bounce models, but they can be boosted in others. If gravitational waves from an earlier cycle make it through the bounce, they might leave a mark on the CMB's polarization pattern. This would be a clear, testable reminder of how things worked before the Big Bang. Simulating a second Big Bang supercomputer models and predictions for a cosmic restart. We can't try our ideas about what a second Big Bang would be like in a lab because the energies, pressures, and timescales involved are too big for us to handle here on Earth. Instead, the best way to study this possibility is to build it inside a machine, a supercomputer that can combine the equations of astronomy, particle physics, and quantum gravity into a picture of a universe dying and then being born again. There are Einstein field equations of general relativity at the heart of these models. These equations show how space-time changes when matter and energy interact with it. But those formulae aren't enough for a second Big Bang situation. Densities get close to the Planck scale near the bounce, which is where quantum effects take over. Physicists use loop quantum cosmology, LQC, asymptotically safe gravity, or some constraints of string theory to describe this. These make it possible to think of space-time as a separate or emerging thing, which stops the problems that come up with classical collapse models when densities go on forever. The first challenge in running such a simulation is resolution. The bounce might happen in as little as 10 to the minus 43 seconds, and involves fluctuations ranging from subatomic to cosmic scales. Capturing how these scales interact requires adaptive mesh refinement, where the simulation automatically boosts resolution in regions of extreme curvature and lowers it in smoother areas. Modern exascale supercomputers, capable of quintillions of calculations per second, are only now making this kind of dynamic range possible. The amount of stuff in the world adds another level of complexity. A good model needs to include dark matter, dark energy, or whatever theory's replacement for it, radiation, baryonic matter, and maybe even strange fields or particles that are only present near the bounce. The Boltzmann equations are used by physicists to study particle interactions. These equations show how particle species scatter, decay, and disappear as the temperature of the world changes. This is very important for guessing whether a new round of nucleosynthesis, the creation of the light elements, would lead to the same chemicals as now, or something completely different. Simulations also probe how cosmological perturbations evolve through the bounce. By seeding the pre-bounce universe with tiny fluctuations in density and curvature, researchers can see which ones survive, which are amplified, and which are erased. The resulting power spectrum can be compared to the one observed in our own cosmic microwave background. If certain features like oscillatory patterns or suppressed large-scale power match across models and data, it could be indirect evidence for a rebirth scenario. Most interestingly, these virtual worlds can test the basic constants by doing what-if studies. Simulations can look at how even small changes would affect the formation of stars, the grouping of galaxies, and the cosmic web by changing things like the fine structure constant or the gravity constant between cycles. This lets us know if the constants in our world are perfectly tuned, or if they could change naturally from cycle to cycle, while still making complex structure. Visualizing the results is as important as the raw computation. Many teams convert the simulation output into synthetic sky maps, showing what the universe would look like in microwaves, infrared, or gravitational waves immediately after the bounce and billions of years later. These visualizations serve not just as scientific tools, but also as guides for where and how to search for signatures of past cycles in real data. While no simulation can claim to be an exact copy of the world, they are useful for testing theories. Different models, such as Ekpyrotic contraction and vacuum decay triggers, can be run with the same starting conditions to see how their forecasts are different. If one model regularly makes features that we could see today, it goes up the list of possible bounce mechanisms. Quantum computing could change this area even more in the next 10 years as it gets better. Quantum computers naturally work well with simulating quantum systems. This could make it possible to directly model the quantum state of the world during the bounce, instead of using rough equations. These kinds of models might show completely new behaviors, maybe even routes you wouldn't expect for information or structure to move from one cycle to the next. Observational windows for detecting a coming rebirth. If there is going to be a second Big Bang, there won't be a cosmic time clock to let us know. They'll be buried in the sky, hidden in small changes, weak signs, and rare alignments that can only be picked up by the most sensitive equipment. Astronomers are trying to figure out which of these signs really mean that the universe is about to go through a cycle of collapse and return, and which are just noise caused by the universe changing. CMB, or the cosmic microwave background, is one of the most direct ways to look into things. Some theories think that small oddities like hemispherical power imbalances, cold spots, and strange alignments found on precise maps from missions like Planck could be leftovers from a previous cycle. In the next 10 years, next-generation CMB telescopes like LightBird and CMB-S4 will make it possible to look for even fainter signs. This includes strange polarization patterns or oscillating parts in the power spectrum that could mean that perturbations from a universe before the bounce are still there. Beyond microwaves, gravitational wave detectors could be game changers. If the universe has bounced before, relic gravitational waves from the prior contraction or bounce phase might still be traveling through space-time. Space-based observatories like LISA, Laser Interferometer Space Antenna, and its successors could search for these low-frequency ripples. They'd be looking for a stochastic background, a steady hiss of space-time distortion, with a spectral shape that doesn't match inflationary predictions, but aligns with cyclic models. Large-scale galaxy surveys are another crucial window. If the current universe is subtly preparing for contraction, its large-scale structure might begin evolving in ways that don't match standard dark energy expectations. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will track billions of galaxies over 10 years, mapping their positions and motions with unprecedented accuracy. Any deviation in the expansion rate, a slowing where acceleration is expected, could hint at new physics driving the universe toward a reversal. Exact spectroscopy is another important factor. The high-resolution spectrographs on the Extremely Large Telescope, ELT, will measure the absorption lines of faraway quasars to see if basic constants like the fine structure constant alpha are changing over time. Scalar fields may be changing beneath the surface, causing a slow drift. These are the same fields that could finally change the direction of cosmic growth from outward to inward. In the high-energy domain, gamma-ray and X-ray telescopes could search for exotic particle signatures that might emerge as dark energy evolves. The appearance of new, unstable particle species or an unexpected change in the cosmic ray spectrum might signal a transition in the vacuum state, potentially a prelude to a vacuum decay event capable of initiating a new cosmic era. Neutrino observatories could also play a part. The Relic neutrino background, a faint whisper from the first seconds of our universe, may carry distortions if it has been shaped by processes before the Big Bang. Proposed detectors like Ptolemy aim to capture these ultra-low energy neutrinos. If their energy distribution or directional patterns deviate from standard cosmology, it could point toward physics that bridges cycles. Even the timing of pulsars, nature's most precise clocks, offers a surprising route. By tracking the arrival times of pulses from millisecond pulsars across the galaxy, astronomers can detect incredibly small changes in spacetime. A coordinated drift in these timings across the sky could betray the influence of a large-scale contraction or a growing anisotropy in the universe's expansion. All of these things would not show that a new beginning is coming by themselves. When multiple, separate signs start to point to the same underlying change in cosmic dynamics, that is when the power of convergence occurs. Because of this, many of these tasks are planned to happen at the same time, allowing data to be joined and checked against each other. It will be hard to figure out what the data means. Some tiny changes in the CMB's polarization could be caused by cosmic dust lensing, or they could be the mark of a universe that has been here before. A small decrease in the speed of cosmic growth might just be a change in the numbers, or it could be the first sign that the universe is crumbling. It will take years of careful study, imagination, and care to tell the difference between everyday astrophysical causes and really radical cosmological meanings. There may be a new beginning for the universe. If this is true, then every star we see, every galaxy we map, and every tiny ripple in the cosmic background is part of a much bigger cycle that will last longer than us, our world, and even our current laws of physics. If we think about the idea of a second Big Bang, our place in time changes. We see it as just one picture in an endless cosmic loop. We might not live to see the next birth, but we can still listen for its first sounds in the sky right now. Share your thoughts in the comments below, right here on Beyond Horizons, if you want to keep discovering these new areas with us. Don't forget to like and follow.